The universe is vast, mysterious, and filled with wonders that push the boundaries of our understanding. Among its most enigmatic phenomena are black holes, regions of space where gravity is so intense that nothing, not even light, can escape. For centuries, these cosmic objects remained hidden, shrouded in mystery, known only through theory and imagination. The idea of black holes emerged from Albert Einstein's theory of general relativity, a revolutionary framework that redefined how we perceive space and time. It described how massive objects warp the fabric of the universe, creating gravitational wells that can trap anything falling within their grasp. But for decades, black holes were just a concept, something scientists believed in but could never see. Imagine a place where the rules of physics as we know them break down, where time stretches and matter collapses into an infinitely dense point. These are the black holes at the centers of galaxies, surrounded by swirling disks of gas and dust that glow brilliantly as they spiral inward. They're invisible directly, but their impact on nearby stars and light gives us clues to their existence. The question remained, could we ever capture a black hole in an image? It seemed impossible. Black holes are far away, small compared to the vastness of space and hidden by layers of dust and gas. But science thrives on challenges, and researchers around the world set out to achieve what had never been done before. At the heart of this mission was the Event Horizon Telescope, a global network of radio telescopes working together to act as a single Earth-sized lens. By linking observatories across continents, scientists hope to overcome the limitations of distance and scale, peering into the depths of the cosmos to uncover one of its greatest secrets. The Event Horizon Telescope aimed to capture the event horizon, the boundary surrounding a black hole where light and matter are pulled in and can no longer escape. This edge is the black hole's silhouette, the shadow cast against the glowing backdrop of its accretion disk. If we could see that, we could see the unseeable. The target was M87*, a supermassive black hole located 55 million light-years away in the Virgo galaxy cluster. This colossal object, billions of times the mass of our Sun, was an ideal candidate for the first attempt at imaging a black hole. Its immense size and brightness made it a promising focus for the Event Horizon Telescope's ambitious goals. Months of preparation and observation followed, with teams collecting terabytes of data from telescopes worldwide. The information was so vast it couldn't be sent over the internet. It had to be physically transported on hard drives to centralized processing centers. There, powerful algorithms and supercomputers transformed the raw signals into a coherent image. Then came the moment of truth. After years of effort, the first ever image of a black hole was unveiled. It wasn't a sharp photograph, but a blurry, glowing ring surrounding a dark center, the shadow of M87*, seen for the first time. This groundbreaking image confirmed decades of theory and brought the invisible into view. This achievement was more than just a technical milestone. It represented the power of collaboration, the ingenuity of human minds, and our unyielding curiosity to explore the unknown. The first picture of a black hole opened a window into a realm of physics that had previously only been imagined, marking a new era in our understanding of the universe. Black holes are among the most fascinating and perplexing phenomena in the universe. Defined as regions where gravity is so intense that not even light can escape, they defy the laws of nature as we understand them. These cosmic enigmas challenge our perception of space, time, and the very fabric of reality. At their core lies a singularity, an infinitely dense point where all the black hole's mass is concentrated. Surrounding it is the event horizon, the invisible boundary that marks the point of no return. Anything crossing this threshold is forever lost, drawn inexorably into the black hole's depths. The event horizon is what gives black holes their name, as it effectively cloaks everything within from view. Light emitted from just outside this region interacts with the immense gravity, creating a distinct silhouette. Capturing this shadow offers a way to observe the unobservable. Black holes vary in size and type, from stellar remnants a few times the mass of the Sun to supermassive giants at the centers of galaxies. These larger black holes, like M87*, dominate their surroundings, influencing the behavior of stars, gas, and light over immense distances. They are not merely destructive, they also shape the growth and evolution of galaxies. Despite their fearsome reputation, black holes are vital to the cosmic ecosystem. Their intense gravity helps regulate star formation, recycle matter, and even spark the birth of new stars. Without them, the universe might look very different from the one we know today. Understanding black holes is more than a matter of scientific curiosity. It's a quest to comprehend the underlying principles of the cosmos. They embody the extremes of nature, testing our theories and pushing the boundaries of human knowledge. From relativity to quantum mechanics, black holes bridge some of the most profound areas of physics. The significance of the event horizon lies in its role as a boundary between what can and cannot be observed. It is the line that separates the visible universe from the hidden interior of a black hole. By studying this boundary, we gain insights into the behavior of matter and energy under the most extreme conditions imaginable. Black holes are not empty voids, but active regions of space-time that interact with their surroundings. As they consume matter, they release enormous amounts of energy, powering some of the brightest phenomena in the universe. Quasars, for example, owe their brilliance to the voracious appetite of supermassive black holes. In capturing the first image of a black hole, scientists focused on the interplay between the event horizon and the glowing accretion disk of matter spiraling toward it. This light, distorted and bent by the black hole's gravity, creates the iconic ring structure we see. It's a snapshot of the immense forces at work in these cosmic engines. The significance of this achievement extends beyond the black hole itself. It provides a real-world laboratory for testing Einstein's predictions about the warping of space and time. Every detail of the captured image aligns with theoretical models, validating decades of research. This discovery also opens doors to exploring unanswered questions about the universe. What happens at the singularity? How does quantum mechanics integrate with the gravitational forces of a black hole? The first image is just the beginning of a journey into the unknown. As we delve deeper into these cosmic mysteries, black holes serve as a reminder of humanity's relentless drive to uncover the secrets of the universe. They are not just objects of scientific study, but symbols of the unknown, challenging us to explore and understand the farthest reaches of existence. Gravity is the defining force of a black hole, shaping its structure and governing its behavior. It's not just powerful, it's absolute, dominating everything in its vicinity. This immense gravitational pull bends light and distorts space, creating the phenomena we associate with black holes. The event horizon is where gravity takes complete control. Beyond this boundary, escape becomes impossible, no matter how fast you travel. It's the point where the warping of space-time becomes so extreme that it traps anything crossing into it. This gravitational power originates from the black hole's mass, concentrated into an incredibly small volume. The denser the black hole, the stronger its gravitational effects. It's this density, not just its size, that makes a black hole's pull so inescapable. Close to the event horizon, gravity doesn't just pull, it stretches and compresses. This process, called spaghettification, elongates objects as they approach the black hole. It's a dramatic reminder of the forces at play near these cosmic titans. The gravity of a black hole also influences its surroundings, extending its effects far beyond the event horizon. Stars orbit at astonishing speeds, drawn by the black hole's invisible grip. Even light traveling near a black hole follows curved paths, creating visual distortions. This distortion of light creates the black hole's shadow, a dark void surrounded by a glowing ring of warped light. The shadow is a direct consequence of gravity bending and trapping light. Observing this shadow gives scientists the clearest evidence of a black hole's existence. Gravity also powers the accretion disk, the swirling material spiraling into the black hole. Friction and heat generated in the disk produce intense radiation, making these regions some of the brightest in the universe. This energy is entirely fueled by the black hole's gravitational pull. On larger scales, black hole gravity influences galaxies, anchoring their cores and shaping their evolution. Supermassive black holes can affect star formation and even regulate the flow of matter in their host galaxies. They act as cosmic engines driven entirely by gravity. Einstein's theory of general relativity describes how gravity works near black holes. It predicts how space and time warp under extreme mass, and these predictions align with observations of black holes. The first image of M87* provided crucial confirmation of these theoretical models. Black hole gravity even affects time itself, slowing it down near the event horizon. This phenomenon, known as time dilation, means that time passes differently for an object close to the black hole compared to one far away. It's a striking example of the interplay between gravity and the nature of time. By studying black hole gravity, we're not just learning about these objects, we're uncovering fundamental truths about the universe. Gravity, as observed near a black hole, offers a window into the behavior of space-time itself. It's a force that defines not only the black hole, but also the fabric of reality around it. These gravitational effects are what make black holes so unique and so crucial to our understanding of the cosmos. Their gravity is not just a feature, it's the very essence of what they are, a force that continues to challenge and inspire our exploration of the universe. Observing the event horizon of a black hole is a monumental challenge. These regions are incredibly small compared to the vast distances that separate us from them. The farther the black hole, the finer the detail needed to detect its faint and elusive outline. Intervening matter further complicates the task. Gas, dust, and other cosmic materials obscure our view, scattering light and distorting the signals we rely on. Filtering through this interference requires extraordinary precision and advanced observational tools. The immense gravitational field of the black hole bends light around it, creating a distorted image of the event horizon. While this bending helps make the shadow visible, it also complicates interpreting the data. Every observation must account for this gravitational lensing. Black holes emit no light of their own, making them effectively invisible against the backdrop of space. The only detectable features are the bright emissions from the surrounding accretion disk and the shadow they cast. This means scientists are working with indirect evidence, piecing together a picture from surrounding effects. The size of the event horizon is another hurdle. Even for a supermassive black hole like M87*, the shadow appears incredibly small from Earth's perspective. Capturing an image with enough resolution to see it requires an observational tool the size of our planet. To overcome this, scientists created the Event Horizon Telescope, a network of radio telescopes spanning the globe. Synchronizing these observatories was a major challenge, as they had to function as one cohesive system. Precision timing and data alignment were critical to achieving this unified view. The Earth's atmosphere also interferes with observations. Radio waves from distant objects are distorted as they pass through layers of air. Advanced algorithms are needed to correct for these distortions, ensuring the signals retain their original clarity. Collecting data across such a large network presented logistical challenges. Each telescope generated massive amounts of information, far too much to transmit electronically. Instead, the data was stored on physical hard drives and transported to central processing centers for analysis. Processing the data required unprecedented computational power. Specialized algorithms were developed to combine signals from all the telescopes into a single coherent image. This process involved eliminating noise, aligning data streams, and reconstructing the faint signature of the black hole. Weather conditions and the rotation of the Earth added further complications. Telescopes could only observe the target for limited windows, and poor weather could disrupt the process entirely. Coordinating ideal conditions across multiple sites was a delicate and unpredictable task. Despite these difficulties, the imaging team faced an additional challenge, distinguishing the true signal from background noise. The data collected was incomplete, requiring sophisticated mathematical techniques to fill in the gaps. Even with state-of-the-art tools, success was never guaranteed. All of these obstacles highlight the extraordinary effort required to observe something as elusive as the event horizon. It took years of preparation, international collaboration, and cutting-edge innovation to turn a theoretical boundary into an image we could see and study. The Event Horizon Telescope is a groundbreaking project designed to image black holes by turning the entire Earth into a virtual telescope. This was achieved by linking observatories around the globe, creating an instrument capable of unprecedented resolution. Together, these telescopes acted as one, targeting the faint and distant signals of black holes. The concept relies on a technique called Very Long Baseline Interferometry, or VLBI. This method combines signals from multiple telescopes, allowing scientists to create a single, detailed image. The larger the distance between the telescopes, the finer the detail they can resolve. Each telescope in the network operates independently, collecting radio waves emitted from the region around a black hole. These waves are generated by the hot, glowing matter in the accretion disk. By synchronizing their observations, the telescopes effectively form a lens the size of the planet. A key challenge was timing. The telescopes needed to record their data simultaneously, down to fractions of a second. To achieve this, atomic clocks were used at each site, ensuring the observations were perfectly synchronized across thousands of miles. The data collected was enormous, petabytes of information from each observing run. This volume was far too large to transmit digitally, so it was stored on specialized hard drives. These drives were then shipped to central processing centers, where the data from all the telescopes could be combined. Processing this data required innovative algorithms to piece together a coherent image. The signals from each telescope had to be carefully aligned, accounting for differences in timing, atmospheric conditions, and noise. This step was crucial for reconstructing the image of the black hole's shadow. The EHT relies on observing radio waves, which can pass through dust and gas that block visible light. This makes it possible to peer into regions otherwise obscured. By focusing on these wavelengths, the team could capture the glow of the accretion disk surrounding the event horizon. The network included telescopes in diverse locations, from mountaintops to deserts, each chosen for its clear skies and minimal interference. These sites spanned continents, from North America to Europe, South America, and Antarctica. Together, they formed a global web of observation. Collaboration was at the heart of the EHT. Hundreds of scientists from around the world worked together, pooling their expertise to tackle the technical and logistical challenges. This project was a testament to the power of international teamwork and shared ambition. The concept of the EHT wasn't just about linking telescopes, it was about pushing the boundaries of what's possible. It required breakthroughs in technology, from data storage to signal processing, and the ability to think on a planetary scale. This vision turned an idea into reality. By using Earth's rotation, the EHT could gather data from different angles over time. This process enhanced the resolution, filling in gaps in the observations. It was like painting a picture of the universe, one brushstroke at a time. The Event Horizon Telescope concept demonstrates what humanity can achieve with determination and ingenuity. By combining resources and expertise from across the globe, it created a window into the most extreme regions of the cosmos. This approach not only revealed the first black hole image, but also opened the door to countless future discoveries. Theoretical predictions about event horizons come directly from Einstein's theory of general relativity. This theory describes how massive objects warp space-time, creating a gravitational well. In the case of black holes, this well becomes so deep that it forms a boundary from which nothing can escape. The event horizon itself is not a physical surface but a mathematical concept. It marks the point where the escape velocity exceeds the speed of light. Beyond this boundary, space-time curves infinitely inward, trapping everything that crosses it. Scientists predicted that the event horizon would cast a shadow against the glow of the surrounding accretion disk. This shadow, a direct consequence of the intense gravitational warping of light, would appear as a dark silhouette. The size and shape of this shadow could be calculated using relativity. One key prediction is that the shadow should be nearly circular for a black hole that isn't rotating too quickly. The shape is influenced by the spin of the black hole, with faster rotation causing the shadow to stretch slightly. Observing this distortion allows scientists to infer the black hole's spin and orientation. The presence of the event horizon creates a photon sphere, a region where light orbits the black hole. Theoretical models suggest that this photon sphere contributes to the brightness of the glowing ring around the shadow. Its behavior aligns closely with the predictions of Einstein's equations. General relativity also predicts how matter behaves as it approaches the event horizon. The intense gravitational forces cause matter to heat up, emitting radiation in the process. The glowing accretion disk around a black hole matches these predictions, providing indirect evidence of the event horizon's existence. The theory anticipates that time slows near the event horizon due to gravitational time dilation. From an outside perspective, an object falling toward the black hole appears to freeze, never quite crossing the horizon. This effect, though unobservable in practice, fits perfectly with relativity's framework. Simulations of black hole environments have modeled how light bends around the event horizon. These simulations predicted the exact ring-like structure revealed in the first black hole image. This confirmation demonstrated that our theoretical understanding of black holes was accurate. The event horizon is also predicted to have no physical texture, described as a smooth boundary with no irregularities. This property, known as the no-hair theorem, means black holes are defined only by their mass, spin, and charge. Observations of black hole shadows support this idea. Quantum mechanics adds another layer of complexity to these predictions. Theoretical models suggest that quantum effects near the event horizon could create subtle variations in how black holes emit radiation. These effects remain largely untested but could provide new insights into fundamental physics. The size of the event horizon depends on the black hole's mass, with supermassive black holes having horizons millions of kilometers across. The predictions align with observations of the shadow scale in relation to M87*. This agreement between theory and observation is a triumph of modern physics. Each theoretical prediction builds on the assumption that space-time behaves according to Einstein's equations. By imaging the event horizon and comparing the results to these models, scientists have validated many of these predictions. Yet mysteries remain, and each discovery brings us closer to understanding the full reality of black holes. The Event Horizon Telescope collaboration brought together scientists and institutions from across the globe. This unprecedented partnership united astronomers, physicists, engineers, and data scientists in a common goal. It was a demonstration of international cooperation at its finest. The collaboration spanned more than 20 countries and included hundreds of researchers. Each team contributed expertise, from designing equipment to developing algorithms. This diversity of skills was essential to overcoming the challenges of observing a black hole. Participating telescopes were located on every continent, including remote sites like Antarctica. These observatories were operated by local teams who maintained the equipment and ensured precise data collection. Each location added a critical piece to the global puzzle. Funding for the project came from multiple sources, including government agencies, research institutions, and private organizations. Securing these resources required significant effort and a shared belief in the importance of the mission. Without this financial support, the collaboration would not have been possible. Coordinating so many telescopes required meticulous planning. Each observatory had to align its schedule to observe the target at the same time. This synchronization ensured that the data could be combined into a single image. Communication was a cornerstone of the collaboration. Teams across different time zones had to share updates, troubleshoot problems, and discuss findings in real time. Regular meetings and conferences kept everyone on the same page. The project also relied on shared technology and innovation. Custom-built equipment was used to capture the faint radio signals from the black hole. These tools were designed collaboratively, with input from scientists and engineers worldwide. The processing of data involved centralized efforts in major computing hubs. Teams worked around the clock to analyze the terabytes of information collected. This stage of the project was a testament to the power of teamwork and shared resources. Cultural and linguistic differences among the collaborators were embraced as strengths. Scientists from diverse backgrounds brought unique perspectives and problem-solving approaches. This inclusivity enriched the project and fostered a sense of global unity. The success of the Event Horizon Telescope collaboration has inspired future projects. It showed that large-scale international efforts are not only possible, but essential for tackling complex scientific challenges. This model is now being applied to other areas of research. The image of the black hole was not just the result of technology, but of human dedication and partnership. Every pixel in that image represents the combined efforts of countless individuals working toward a shared vision. It's a testament to what can be achieved when the world comes together. The Event Horizon Telescope collaboration reminds us that science transcends borders. It's a universal language that connects people in pursuit of knowledge. This achievement is as much about the human spirit as it is about the cosmos. Radio telescopes play a critical role in capturing the faint signals emitted by regions around black holes. Unlike visible light, radio waves can pass through clouds of gas and dust, providing a clearer view of otherwise obscured areas. This makes them indispensable for studying the environment near an event horizon. These telescopes detect electromagnetic waves at radio frequencies, which are much longer than visible light waves. By capturing these signals, they allow scientists to observe phenomena invisible to traditional optical telescopes. This capability is essential for studying black holes, which emit no light of their own. Each radio telescope in the Event Horizon Telescope network contributed to forming a massive virtual observatory. By working together, these instruments achieved a resolution equivalent to a telescope the size of the Earth. This collaboration allowed them to detect details as small as the shadow of a black hole. The locations of the telescopes were carefully chosen to optimize coverage. From the high deserts of Chile to the icy expanses of Antarctica, each site offered clear skies and minimal interference. These conditions ensured the data collected was as accurate and consistent as possible. Radio telescopes work by capturing signals and converting them into digital data. Sensitive receivers amplify the weak waves coming from space, making them strong enough to analyze. This process requires equipment that can detect even the faintest signals from millions of light years away. The signals collected by each telescope are stored as vast amounts of raw data. Because radio waves from a black hole are extremely faint, every bit of information is vital. The telescopes operate at such precision that even tiny environmental factors are taken into account. To align the data from all the telescopes, their observations must be perfectly synchronized. This is achieved using atomic clocks, which keep time with incredible accuracy. Synchronization is crucial for combining the signals into a single coherent image. Atmospheric interference is another challenge for radio telescopes. As signals travel through the Earth's atmosphere, they can be distorted or weakened. Advanced processing techniques correct for these effects, ensuring the final image remains clear and accurate. Each telescope also contributes unique perspectives based on its location. By collecting data from multiple angles, the network creates a more complete picture. This ability to fill in gaps is what makes the Event Horizon Telescope's observations so detailed. The equipment used in these telescopes must withstand extreme conditions. From freezing temperatures to high altitudes, the instruments are designed to perform reliably in some of the harshest environments on Earth. This durability ensures continuous data collection during critical observation windows. Radio telescopes have been pivotal in advancing our understanding of the universe, far beyond black holes. They've revealed the cosmic microwave background, pulsars, and distant galaxies. Their role in the Event Horizon Telescope is just one example of their immense scientific value. By harnessing the power of radio telescopes, scientists turned theoretical predictions into observable phenomena. These instruments bridged the gap between imagination and reality, allowing us to see a black hole for the first time. They are the technological backbone of this historic achievement. Synchronizing telescopes across the globe was one of the most critical aspects of the Event Horizon Telescope project. Each observatory had to operate in perfect unison, capturing data at precisely the same moment. This required an extraordinary level of precision and coordination. Atomic clocks were the cornerstone of this synchronization. These devices measure time with extreme accuracy, down to billionths of a second. Every telescope relied on atomic clocks to timestamp the data it collected, ensuring all observations could be aligned later. The rotation of the Earth added another layer of complexity. As the planet turned, each telescope's position relative to the black hole changed. This motion was accounted for in real time, enabling continuous and coordinated observation of the target. Weather conditions at each site also had to be monitored closely. Clear skies were essential for optimal data collection, but the weather could vary dramatically between locations. Teams worked together to identify the best observation windows for all telescopes simultaneously. The telescopes were spread across vast distances, from Chile to Spain, Hawaii to Antarctica. Each location provided a unique vantage point, but the differences in time zones and geography posed logistical challenges. Coordinating operations across these regions required constant communication and meticulous planning. Data synchronization wasn't just about timing, it also involved calibrating the equipment. Each telescope had to operate with identical settings and sensitivity to ensure the signals they captured were consistent. Even minor differences could disrupt the alignment of the final data. To maintain this precision, extensive testing and rehearsal observations were conducted before the actual data collection. These dry runs ensured that every component of the system worked seamlessly. They also helped the teams refine their procedures and address potential issues. The synchronization extended beyond the telescopes to the teams operating them. Scientists, engineers, and technicians had to work in harmony, often during long, sleepless nights. Their ability to coordinate across continents was as vital as the technology itself. After the observations were complete, the synchronization efforts shifted to data processing. The timestamps from each telescope allowed scientists to align the signals, despite the vast distances separating them. This step was crucial for reconstructing a coherent image of the black hole. The precision required for this synchronization highlights the scale of the challenge. Even the smallest error in timing or alignment could compromise the entire project. It was a testament to the ingenuity and dedication of the teams that these hurdles were overcome. This global synchronization represented more than just technical achievement. It symbolized the unity of purpose behind the Event Horizon Telescope. Scientists from different nations and disciplines worked together seamlessly, bound by their shared mission to capture the first image of a black hole. Through this intricate process, the telescopes became more than individual instruments. Together, they formed a single, planet-sized observatory, capable of resolving details at unimaginable distances. This synchronization made the impossible possible, turning a bold vision into a historic reality. The data collected by the Event Horizon Telescope was unlike anything gathered before. Each telescope in the network recorded signals from the target black hole, producing vast amounts of raw data. This information captured the faint radio waves emitted from the region around the event horizon. Because the data was so immense, it couldn't be transmitted over the internet. Instead, it was stored on high-capacity hard drives, specially designed for the project. These drives were physically transported to central processing centers, where the analysis would take place. The two main data processing hubs were located in the United States and Germany. These facilities were equipped with powerful supercomputers capable of handling the enormous datasets. Their role was to combine the observations from all the telescopes into a single unified signal. Each telescope's data came with precise timestamps provided by atomic clocks. These timestamps ensured that the signals could be perfectly aligned during processing. Synchronization was critical to reconstruct the image of the black hole with the highest possible accuracy. The process of combining the data is known as correlation. It involved comparing the signals from each pair of telescopes in the network to identify matching patterns. These patterns held the key to revealing the structure of the black hole's shadow. Noise and interference in the data added another layer of complexity. Atmospheric distortions, equipment sensitivity, and local environmental factors all introduced challenges. Advanced algorithms were developed to filter out this noise and focus on the true signal from the black hole. Processing the data took months of continuous effort. Teams worked in shifts, analyzing and reanalyzing the signals to ensure nothing was overlooked. This meticulous approach was necessary to confirm that the image was accurate and free from errors. The raw data itself was enormous, totaling over 5 petabytes. That's equivalent to millions of high-definition movies. Handling such volumes required innovative storage and computational techniques to keep the information accessible and manageable. Simulations played an essential role during processing. By comparing the real data to theoretical models, scientists could verify their findings. These simulations helped refine the image and provided insights into the behavior of matter near the event horizon. Collaboration was essential during this stage. Teams from different disciplines worked together, combining expertise in astronomy, physics, and computer science. Their collective efforts ensured that every aspect of the data was carefully examined and understood. The final step in the process was creating the image itself. Using specialized imaging techniques, the teams translated the correlated data into a visual representation of the black hole's shadow. This transformation was the culmination of years of work and countless hours of analysis. Data collection and processing were not just technical tasks, they were a bridge between theory and observation. Every piece of information brought scientists closer to understanding one of the most mysterious objects in the universe. This effort turned raw signals into a groundbreaking image, forever changing how we see black holes. Creating the first image of a black hole required breakthroughs in both technology and methodology. Traditional telescopes couldn't achieve the necessary resolution, so the Event Horizon Telescope team had to innovate. They developed tools and techniques that pushed the boundaries of what was scientifically possible. One of the most important innovations was very long baseline interferometry, or VLBI. This method linked telescopes around the globe, effectively creating a virtual telescope the size of Earth. The larger the telescope, the finer the details it can resolve, making this technique essential for imaging the distant black hole. Advanced atomic clocks were crucial for synchronizing the observations from all the telescopes. These clocks kept time so precisely that their margin of error was less than a billionth of a second. Without this level of accuracy, combining the data into a coherent image would have been impossible. The data storage systems were also cutting edge. Custom-designed hard drives capable of handling petabytes of data were built specifically for the project. These drives allowed the team to transport enormous volumes of information to processing centers efficiently. Innovative algorithms played a vital role in turning the raw data into a usable image. These algorithms were designed to handle incomplete and noisy data, filling in gaps and reducing interference. They transformed faint radio signals into a clear representation of the black hole's shadow. Simulations were another critical innovation. Scientists ran thousands of models to predict what the black hole's shadow might look like under different conditions. These simulations helped refine the imaging process and confirm that the final results matched theoretical expectations. The telescope receivers themselves were specially designed to detect faint radio waves from deep space. These highly sensitive instruments could pick up signals that would otherwise be drowned out by background noise. Their precision ensured that no detail was lost during observation. The global network of telescopes was equipped with cutting-edge hardware to withstand harsh environments. From the freezing temperatures of Antarctica to the high altitudes of Chile, each site was prepared to operate under extreme conditions without compromising performance. Data correlation required the use of some of the world's most powerful supercomputers. These machines processed the vast amounts of data collected, comparing signals from each telescope and aligning them to create a single dataset. The computational power needed for this task was unprecedented. Collaboration tools also represented an innovation. Scientists across the globe used advanced communication platforms to share data, discuss findings, and solve problems in real time. This seamless connectivity allowed the project to move forward without delays. The imaging process itself was an achievement in innovation. Techniques like clean imaging and maximum entropy method were used to reconstruct the black hole's shadow from the processed data. These approaches ensured that the image was both accurate and representative of the real object. The technologies developed for the Event Horizon Telescope have applications beyond black hole imaging. They're now being used to study other celestial phenomena, refine observational techniques, and inspire future advancements. These innovations have left a lasting legacy in the field of astronomy. The black hole at the center of the galaxy M87 is both massive and incredibly distant. Located 55 million light-years from Earth, it's one of the largest supermassive black holes ever observed. Its immense scale and distance make it a unique but challenging target for observation. This black hole, known as M87*, has a mass equivalent to over 6 billion suns. Its event horizon spans roughly 40 billion kilometers, a size that defies comprehension. Despite its enormous dimensions, its vast distance causes it to appear smaller than a pinhead in the sky. To put this in perspective, imaging M87* from Earth is like trying to photograph an orange on the surface of the moon. Its apparent size in the sky is incredibly tiny, requiring a resolution far beyond what traditional telescopes can achieve. This challenge defined the scope of the Event Horizon Telescope project. The distance also means that the light captured by the telescopes is ancient. The image we see today shows M87* as it was 55 million years ago, long before humans walked the Earth. Observing something so distant offers a glimpse into the universe's distant past. Even though it's far from us, the black hole's gravitational influence is immense. It affects the motion of stars and gas in its host galaxy, extending its reach across millions of light-years. These indirect effects made it possible to infer the black hole's existence long before it was imaged. The sheer size of M87* contributes to its suitability as a target. Its vast event horizon produces a larger shadow, making it easier to detect than smaller black holes. This is one reason why it was chosen over closer black holes, such as Sagittarius A* at the center of our Milky Way. Distance also introduces complications for data collection. Signals from M87* travel across space, weakening as they spread out over time. Capturing these faint signals requires highly sensitive instruments and a global network of synchronized telescopes. The curvature of space-time around M87** adds another layer of complexity. Its massive gravity bends light, magnifying the region around the event horizon. This gravitational lensing allows us to see the shadow, but it also distorts the image, requiring careful analysis to interpret. The size and distance of M87** demanded the highest possible resolution from the Event Horizon Telescope. To achieve this, the network combined data from observatories across the planet. This technique allowed scientists to effectively zoom in on the black hole despite its distance. The long travel time of light from M87** also means that minor changes in its environment go undetected. What we see in the image is a snapshot of a relatively stable structure. Any dynamic activity, such as matter falling into the black hole, would be too gradual to notice over the timescale of observation. Its distance makes it a fascinating subject for both astrophysics and cosmology. Observing M87** helps scientists study the behavior of light, gravity, and matter on the largest scales. It provides a unique laboratory for testing the limits of current theories about the universe. By capturing the image of M87**, scientists overcame the barriers of size and distance to achieve something extraordinary. The black hole's scale, combined with its remote location, underscores the monumental effort required to make it visible to humanity for the first time. Interference from cosmic dust is one of the significant obstacles in observing black holes. This dust exists in the vast regions between stars and galaxies, scattering and absorbing light. Its presence creates a natural barrier that obscures the faint signals we need to detect. Radio waves, unlike visible light, can penetrate much of this cosmic dust. However, even these signals are affected by scattering, which can distort the image. Correcting for these distortions requires advanced algorithms and detailed modeling of the interstellar medium. The dust isn't evenly distributed, adding to the complexity. Dense regions can block or scatter more radiation, while less dense areas allow clearer signals to pass through. Mapping the dust along the line of sight is essential for understanding how it affects the observations. Interference is especially problematic when observing objects as distant as M87**. The radio waves travel millions of light-years, passing through countless regions of dust. Each layer contributes to the signal degradation, compounding the challenge of capturing a clear image. Dust also emits its own radiation, which can interfere with the faint signals from the black hole's surroundings. This background noise must be filtered out during data processing to isolate the actual emissions from the event horizon region. It's a meticulous and time-consuming process. The properties of the dust, such as its composition and size, influence how it interacts with light. Different wavelengths of radiation are scattered or absorbed in varying ways. By studying these interactions, scientists can refine their techniques to minimize the impact of the dust. Regions of intense star formation, often rich in gas and dust, add another layer of interference. These areas produce significant amounts of radiation that can overshadow the weak signals from a black hole. Careful selection of observation wavelengths helps mitigate this problem. The dust also interacts with the black hole's accretion disk, altering the radiation emitted from the region. This interaction can create patterns that mimic features of the black hole's shadow, complicating the interpretation of the data. Understanding these effects is crucial for accurate imaging. Interference isn't limited to cosmic dust. There's also the influence of planetary and atmospheric noise. Earth's atmosphere contributes additional distortions, requiring further corrections. These combined factors make the task of isolating the black hole's signal incredibly intricate. To address the challenges of cosmic dust, scientists use multi-wavelength observations. By collecting data at various frequencies, they can better distinguish between the true signal and the distortions caused by dust. This approach increases the reliability of the final image. Simulations play a key role in overcoming these obstacles. By recreating the conditions of cosmic dust and its effects on light, researchers can predict and correct for distortions. These models guide the data processing and help verify the accuracy of the image. Despite the interference from cosmic dust, the Event Horizon Telescope succeeded in revealing the shadow of M87**. This achievement demonstrates the power of innovation and persistence in overcoming the natural barriers of the universe. It's a remarkable feat of science and engineering, Earth's atmosphere poses a significant challenge when observing distant cosmic objects like black holes. As radio waves from space travel through the atmosphere, they are distorted by variations in air pressure, temperature, and water vapor. These fluctuations can blur the signals, making it harder to capture clear data. The effect is even more pronounced at higher altitudes where the atmosphere is thinner but more dynamic. Wind currents and shifting layers of air add unpredictable distortions. These atmospheric variations must be accounted for in real time during observations. Water vapor is particularly problematic for radio astronomy. It absorbs and scatters radio waves, weakening the signal by the time it reaches the ground. Sites for telescopes are carefully chosen to minimize this interference, often located in dry, high-altitude regions. Each telescope in the Event Horizon Telescope network faced unique atmospheric conditions. Observatories in the Andes, Hawaii, and Antarctica all operated under vastly different weather systems. Calibrating the data to account for these variations was critical for combining the signals. The atmosphere also limits the time available for observation. Clear skies are essential, but even minor cloud cover can disrupt the collection of radio waves. Scientists worked within narrow windows to ensure the best possible conditions for each observing session. Advanced techniques were developed to correct for atmospheric distortions. By monitoring weather conditions and using calibration tools, scientists could adjust the data to compensate for these effects. These corrections were vital for maintaining the accuracy of the final image. The rotation of the Earth further complicates the problem. As the planet turns, the angle of observation changes, altering the path radio waves take through the atmosphere. This requires constant adjustments to maintain consistent data quality. The presence of the ionosphere, a charged layer of the atmosphere, adds another layer of interference. It can refract and scatter radio waves, especially at lower frequencies. Special algorithms were needed to filter out the distortions caused by this layer. Even the equipment itself is affected by atmospheric challenges. Temperature changes can cause slight shifts in the alignment of telescopes, further complicating data collection. Engineers designed the instruments to withstand these conditions, ensuring reliable performance. Atmospheric noise, or static, is another factor that can mask faint signals. This noise comes from both natural and human-made sources, blending with the data scientists are trying to capture. Filtering out this noise requires sophisticated signal processing techniques. Despite these challenges, the Event Horizon Telescope achieved remarkable precision. By combining data from multiple locations and using advanced corrections, the team overcame the distortions caused by the atmosphere. Each adjustment brought them closer to revealing the shadow of the black hole. The success of this effort highlights the importance of adapting to the limitations of Earth's environment. By addressing atmospheric challenges head-on, scientists were able to transform weak and distorted signals into groundbreaking discoveries. This work demonstrates the resilience and ingenuity required for astronomical research. Coordinating the international efforts of the Event Horizon Telescope required unprecedented levels of collaboration. With telescopes and teams spread across the globe, every detail needed to be synchronized. Communication was key to ensuring the success of this complex endeavor. Each participating observatory had its own unique challenges, from location-specific weather conditions to regional infrastructure. Teams at each site worked tirelessly to address these issues while staying aligned with the broader project goals. This required seamless coordination across continents and time zones. Regular meetings were held to share updates, discuss progress, and troubleshoot potential problems. These meetings often spanned different languages, cultures, and scientific disciplines. The shared commitment to capturing the first image of a black hole united everyone involved. Data collection was only one part of the equation. Coordinating the transport and processing of massive datasets required logistical precision. Hard drives filled with petabytes of information were physically shipped to central processing hubs, where teams worked together to align and analyze the data. Time was another critical factor. The telescopes needed to observe the black hole simultaneously, requiring precise synchronization across all locations. Atomic clocks at each site ensured that every observation was perfectly timed, down to fractions of a second. Funding and resources for the project were drawn from multiple countries and institutions. This required navigating different funding mechanisms and research priorities. Despite these challenges, The project secured the support needed to achieve its ambitious goals. Cultural and institutional differences among the teams were embraced as strengths. Each group brought unique perspectives and expertise to the collaboration. This diversity enriched the project and ensured a comprehensive approach to solving its many challenges. The technical teams faced the daunting task of aligning equipment and protocols across vastly different environments. Telescopes in deserts, mountaintops, and polar regions all needed to function as one. Engineers and scientists worked together to standardize operations without compromising local requirements. Global collaboration extended beyond the science itself. Public outreach efforts were coordinated to share the project's progress and findings with the world. By engaging communities worldwide, the team inspired excitement and support for their groundbreaking work. The success of the Event Horizon Telescope depended on trust and teamwork. Each participating institution relied on the others to uphold their responsibilities and deliver results. This mutual reliance fostered a sense of camaraderie among the global team. Overcoming language barriers was another significant achievement. Scientists from diverse linguistic backgrounds developed shared terminologies and communication methods. This allowed for clear and effective collaboration despite differences in language and culture. The coordination of international efforts demonstrated the power of science to transcend borders. The Event Horizon Telescope became a symbol of what humanity can achieve when working together toward a common goal. It showed that collaboration is not just a tool but a driving force for discovery. The immense amount of data collected by the Event Horizon Telescope presented unprecedented storage and analysis challenges. Each telescope generated petabytes of information during the observation period. Managing, transporting, and processing this data required innovations in both hardware and software. Because the volume of data was too large to transmit digitally, it had to be physically stored on specialized hard drives. These drives were then shipped to central processing facilities, a process that demanded careful handling and secure transport. Any loss or damage to the drives could jeopardize months of effort. Each hard drive was designed to handle the unique demands of the project. They needed to store high-fidelity radio signals without compression, preserving the integrity of the data. The sheer quantity of drives required careful cataloging to keep track of every piece of information. Synchronizing data from multiple telescopes was one of the most complex hurdles. Each observatory recorded signals independently, and these recordings needed to be perfectly aligned. The timestamps provided by atomic clocks were essential for combining the data accurately. Noise and interference in the raw data added another layer of complexity. Natural and artificial sources of static could obscure the faint signals from the black hole. Advanced filtering techniques were developed to isolate the desired signals while removing distortions. Processing this data required the use of some of the world's most powerful supercomputers. These machines performed billions of calculations to correlate the signals from each telescope. Without this computational power, transforming the raw data into a coherent image would have been impossible. The algorithms used for analysis had to be carefully designed and tested. They needed to handle incomplete datasets and fill in gaps caused by interference or missing observations. These algorithms were continually refined to ensure the final image was both accurate and reliable. The teams processing the data faced the challenge of interpreting vast amounts of complex information. They worked in shifts, analyzing patterns, cross-checking results, and troubleshooting any inconsistencies. This collaborative effort spanned months of intensive work. Simulations were used alongside the real data to validate the results. By comparing the processed data to theoretical models, scientists could confirm that the final image matched expectations. These simulations also helped refine the analysis techniques. Then, storage infrastructure at the processing centers had to accommodate the massive data sets. Redundant systems were implemented to ensure no data was lost during analysis. These systems were designed to handle not only the current project, but also future observations. The human element was critical in overcoming these hurdles. Teams of experts in astronomy, computer science, and engineering collaborated to address every challenge. Their dedication and problem-solving skills were instrumental in turning raw data into a historic image. Despite the hurdles, the data storage and analysis efforts succeeded in creating a clear picture of the black hole's shadow. This achievement demonstrated the importance of innovation and collaboration in handling the complexities of cutting-edge science. Every step of the process was a testament to human ingenuity and determination. M87 was chosen as the target for the first black hole image because of its exceptional characteristics. At the center of the massive Virgo galaxy cluster, M87 hosts one of the largest supermassive black holes ever discovered. Its immense size and brightness made it an ideal candidate for observation. The black hole at the heart of M87, known as M87*, is 6.5 billion times the mass of the Sun. This staggering mass creates a large event horizon, producing a shadow that is easier to detect compared to smaller black holes. Its scale offered the best chance of success for the Event Horizon Telescope. Its location, 55 million light-years away, provided a relatively clear line of sight through space. Unlike some closer targets, M87* is less obscured by intervening gas and dust. This clarity helped reduce the interference that could complicate the observations. M87* is surrounded by a bright and active accretion disk. The matter spiraling into the black hole emits intense radiation, creating a glowing backdrop against which the event horizon's shadow can be seen. This high-energy environment provided the contrast necessary to capture the shadow. Another reason for choosing M87* was its relatively stable appearance. While black holes can be highly dynamic, the massive scale of M87* ensures that changes in its accretion disk occur more slowly. This stability made it easier to capture a clear and consistent image. The jets of material ejected from M87* offered additional insight. These jets, spanning thousands of light-years, are powered by the black hole's rotational energy. Studying these features alongside the shadow gave scientists a more comprehensive view of its activity. Its position within the Virgo cluster made M87* a well-studied object. Decades of prior research provided valuable context for interpreting the new observations. This background knowledge gave scientists confidence in their ability to analyze the data accurately. M87* is among the brightest radio sources in the sky, a critical factor for the Event Horizon Telescope. The brightness of its emissions ensured that the telescopes could detect its signals despite the vast distance. This made it a practical choice for the first attempt at imaging a black hole. The size of the event horizon combined with its distance resulted in an angular size that was just large enough to be resolved. The Event Horizon Telescope's resolution, equivalent to seeing a grain of sand on the moon, was tailored to capture details at this scale. M87* fit these parameters perfectly. Its immense mass also helped validate Einstein's predictions. A supermassive black hole like M87* provides a robust test of general relativity. Observing its shadow and comparing it to theoretical models offered an unprecedented opportunity to confirm the accuracy of these equations. Choosing M87* also showcased the power of the global telescope network. Coordinating observations of such a distant and massive object demonstrated the capabilities of the Event Horizon Telescope. The success of this target affirmed the potential for studying other black holes in the future. M87* was not just a practical choice but an ambitious one. Its distance, mass, and activity represented the challenges and rewards of black hole research. Capturing its image marked a monumental step forward in our understanding of the universe. M87, also known as Messier 87, is located in the Virgo cluster, one of the largest and most massive galaxy clusters in the universe. Situated about 55 million light-years from Earth, M87 is a giant elliptical galaxy, home to billions of stars, clusters, and a supermassive black hole at its center. Its sheer scale and brightness make it one of the most prominent members of the cluster. The galaxy itself spans over 120,000 light-years, making it larger than the Milky Way. Its massive size is reflected in its gravitational influence, which extends far into the surrounding cluster. This dominance over its local environment has earned M87 a central role in studies of galactic evolution. At the heart of M87 lies its supermassive black hole, designated M87*. With a mass equivalent to 6.5 billion suns, it is one of the largest black holes ever observed. This immense size gives M87* an event horizon large enough to be visible from Earth with the right tools. The event horizon of M87* measures roughly 40 billion kilometers across, a scale that is difficult to comprehend. This boundary marks the edge of the black hole's gravitational influence, where nothing, not even light, can escape. Its size is a direct consequence of the black hole's incredible mass. M87 is unique in its location within the Virgo cluster. As a central galaxy, it has accumulated vast amounts of matter over billions of years. This includes stars, gas, and even smaller galaxies that have been absorbed into its structure. This position has contributed to the growth of its black hole. The galaxy is also known for its striking jet, a beam of material ejected from the vicinity of the black hole. This jet extends for thousands of light years, visible across a range of wavelengths. Its presence is a clear indicator of the active processes taking place near M87*. The size and activity of M87 make it a natural focus for astronomers studying supermassive black holes. Its black hole is surrounded by a bright accretion disk where gas and dust spiral inward. This disk emits radiation that provides critical clues about the environment near the event horizon. M87's relatively close proximity to Earth by cosmic standards enhances its value as a research target. While 55 million light-years is an immense distance, it is still close enough for detailed observation. This distance places M87* within the resolving power of the Event Horizon Telescope. The galaxy's central black hole is not just massive, it is also extremely old. Formed billions of years ago, it has likely influenced the formation and evolution of M87 itself. Its size suggests that it has consumed vast amounts of matter over its lifetime, contributing to its growth. M87's elliptical shape and lack of prominent spiral arms set it apart from galaxies like the Milky Way. This structure reflects a history of interactions with other galaxies, including mergers and collisions. These events have played a role in shaping its central black hole and its surrounding features. The black hole's size also creates a gravitational influence that extends far beyond the event horizon. Stars in the central regions of M87 orbit at astonishing speeds, drawn in by the black hole's pull. These orbits provide indirect evidence of the black hole's mass and its dominant presence. M87 stands out not only for its location in the Virgo cluster, but also for the unique features that define it. Its massive size, prominent jet, and supermassive black hole make it a cornerstone of our understanding of the universe's most extreme phenomena. This galaxy continues to provide valuable insights into cosmic evolution and the role of black holes. M87's black hole, M87*, is vastly different from the black holes found in the Milky Way. Its size alone sets it apart, with a mass over 6.5 billion times that of the Sun. In comparison, the Milky Way's central black hole, Sagittarius A*, is about 4 million solar masses, making it much smaller and less influential on a cosmic scale. The event horizon of M87* is significantly larger than that of Sagittarius A*. Measuring around 40 billion kilometers across, M87*'s event horizon dwarfs the relatively small horizon of the Milky Way's black hole. This larger size makes M87* more suitable for direct imaging. M87* resides in a massive elliptical galaxy, while Sagittarius A** is located within a barred spiral galaxy. These distinct environments influence the behavior of the black holes. M87* has a much larger reservoir of surrounding gas and matter to draw from, feeding its accretion disk and powering its activity. The activity levels of the two black holes also differ greatly. M87* is an active, supermassive black hole, emitting powerful jets of radiation and matter. Sagittarius A*, on the other hand, is relatively quiet and inactive, with far less material falling into it at present. M87*'s jet is one of its defining features, extending thousands of light-years into space. This energetic outflow is a sign of its ongoing interaction with its surroundings. Sagittarius A* lacks such a prominent jet, reflecting its more dormant state. The accretion disk around M87* is far brighter and more massive than that of Sagittarius A*. This difference in luminosity is partly due to the greater amount of matter spiraling into M87*. It allows astronomers to observe the disk more easily, providing a clearer view of the event horizon's shadow. The gravitational influence of M87* extends much farther than that of Sagittarius A*. Its immense mass affects the motion of stars and gas throughout the core of M87. In contrast, Sagittarius A's influence is more localized, limited to the central region of the Milky Way. The location of each black hole also contributes to their differences. M87* is part of the dense Virgo cluster, surrounded by other massive galaxies. Sagittarius A* is located in a less crowded region, where its interactions with nearby objects are less intense. Even the age and growth histories of the two black holes are distinct. M87* likely grew through the merger of smaller black holes and the accretion of vast amounts of matter over billions of years. Sagittarius A* has had a quieter history, with fewer opportunities to gain mass at a rapid rate. The timescales of activity around these black holes also differ. Changes in the environment near Sagittarius A* happen more quickly due to its smaller size. For M87*, the immense scale means that any significant changes occur over much longer periods, adding to its stability as a target. The technology needed to study these black holes also varies. Imaging Sagittarius A* requires even higher resolution than M87*, due to its smaller size. M87*, with its larger shadow and greater distance, offered an easier first step for the Event Horizon Telescope. The differences between these black holes highlight the diversity of supermassive black holes across the universe. They remind us that each black hole is shaped by its unique environment, history, and scale, offering distinct insights into the nature of these extraordinary objects. Supermassive black holes are fundamental to the structure and evolution of galaxies. Found at the centers of nearly every large galaxy, these massive objects influence the motion of stars, gas, and dark matter in their vicinity. Their presence is a driving force in shaping the dynamics of the galaxies they inhabit. The mass of a supermassive black hole often correlates with the size of its host galaxy's central bulge. This relationship, known as the black hole-galaxy connection, suggests that black holes and galaxies grow together. Understanding this link provides insights into how galaxies evolve over billions of years. These black holes act as engines for some of the brightest phenomena in the universe. Active supermassive black holes power quasars and blazars, which outshine entire galaxies with their energy output. Their accretion disks and jets make them visible across vast cosmic distances. Jets from supermassive black holes, like the one seen in M87, distribute energy and matter across their galaxies. These jets can heat interstellar gas, preventing it from collapsing into new stars. This feedback mechanism regulates star formation and impacts the long-term development of the galaxy. The gravitational pull of a supermassive black hole stabilizes the orbits of stars in the galactic core. Without this central mass, galaxies might lack the structural cohesion that defines their forms. These black holes act as anchors, holding their systems together. Supermassive black holes also serve as laboratories for testing the laws of physics. The extreme gravity near their event horizons offers a unique environment for studying general relativity and space-time behavior. They provide the ultimate proving ground for theoretical predictions. Their influence extends beyond their immediate surroundings. The radiation and winds they generate can shape the intergalactic medium, affecting neighboring galaxies. This makes supermassive black holes key players in the cosmic web that connects galaxies across the universe. Detecting and studying supermassive black holes helps astronomers measure distances and scales in the cosmos. By observing their effects on nearby stars or their emissions, scientists can estimate the mass of these objects and the galaxies they inhabit. This data refines our understanding of the universe's structure. The formation of supermassive black holes remains one of the biggest questions in astrophysics. Some theories suggest they grew from smaller black holes merging or from the direct collapse of massive gas clouds. Their origins hold clues to the earliest epochs of galaxy formation. Their sheer scale and complexity make supermassive black holes a source of awe and curiosity. They represent the extremes of nature, where physics operates in ways that challenge our understanding. They are both destroyers and creators, consuming matter while shaping the growth of galaxies. Supermassive black holes have a profound impact on cosmology. They influence the distribution of matter, the behavior of light, and the overall structure of the universe. Observing these objects deepens our knowledge of how the cosmos has evolved from the Big Bang to today. Studying supermassive black holes connects us to the grandest scales of existence. They are windows into the past, revealing the processes that built the universe as we see it. Each discovery about these cosmic giants brings us closer to unraveling the mysteries of the cosmos. M87 has been a subject of intense study for decades, long before the first image of its black hole. Its prominent position in the Virgo cluster and its unique features made it a natural focus for astronomers. Observations across multiple wavelengths have revealed its dynamic and complex nature. One of the earliest notable features observed in M87 was its powerful jet. Detected in optical wavelengths and later in radio, X-ray and gamma-ray observations, this jet extends thousands of light-years. It has provided key insights into the processes near the galaxy's central black hole. Radio astronomy has played a significant role in studying M87. Early radio maps showed the structure of the jet and the bright core at the galaxy's center. These findings hinted at the presence of a supermassive black hole long before direct imaging was possible. Observations using the Hubble Space Telescope revealed high-speed motion in the central regions of M87. Stars and gas near the core were found to be moving at extraordinary velocities. These motions were one of the strongest pieces of evidence for the existence of a massive black hole. X-ray telescopes have detected hot gas surrounding M87, heated by the energy released from its central black hole. These emissions reveal the interaction between the black hole and its environment, highlighting the feedback mechanisms that shape the galaxy. The jet itself has been studied extensively across many decades. High-resolution images have shown its helical structure and the knots of material moving outward. These features provide clues about the black hole's spin and the magnetic fields that guide the jet. Infrared studies have explored the distribution of stars and dust in the galaxy. These observations help map the history of star formation in M87 and its interactions with nearby galaxies. They also complement studies of the black hole by providing context about its surroundings. M87 has been a critical target for studies of galaxy mergers. Evidence of tidal interactions and disruptions within its structure suggest a history of absorbing smaller galaxies. These events likely contributed to the growth of its supermassive black hole. The size and brightness of M87 have made it a key object in studies of cosmic distances. By measuring its properties and comparing them to other galaxies, astronomers have refined methods for determining distances on a universal scale. This research ties M87 to the broader understanding of the cosmos. Previous studies of M87's core have revealed fluctuations in brightness over time. These variations, thought to be linked to the activity of the black hole, provide a dynamic view of its behavior. They suggest periods of higher and lower accretion rates, altering the emissions from the central region. The galaxy has also been a focal point for simulations of black hole dynamics. Theoretical models based on M87's observed properties have helped predict what the shadow of its black hole might look like. These simulations guided the efforts of the Event Horizon Telescope. Each layer of observation and analysis has built a detailed picture of M87. Long before the first image of its black hole, it was already one of the best understood galaxies in the universe. These prior studies laid the foundation for the historic achievement of capturing the shadow of M87*. Collecting the data to image M87** required multiple nights of coordinated observations. The Event Horizon Telescope team needed several continuous observation windows to capture enough signals from the black hole's surroundings. Each night's work added crucial pieces to the overall data set. The Earth's rotation played a vital role in the process. As the planet turned, different telescopes in the network moved into position to observe M87*. This created a dynamic baseline, allowing the team to gather data from multiple angles and perspectives. Weather conditions were a constant concern during the observation campaign. Clear skies were essential for each telescope to perform at its best. Teams at every site monitored local conditions carefully, often waiting for precise moments of atmospheric stability. Observing M87** required precise timing across all participating observatories. Atomic clocks synchronized each telescope to the exact same moment, ensuring that all data could be aligned perfectly. Without this synchronization, the global network would not function as a single unit. Each telescope recorded signals in the form of radio waves emitted by the black hole's accretion disk and jets. These signals were faint and scattered across space, requiring the telescopes to operate at peak sensitivity. Data was collected in large volumes, capturing every detectable nuance. Because M87** is so distant, The signals arriving at Earth were incredibly weak. It took multiple nights to gather enough data for a clear image. Repeated observations ensured that the team captured as much information as possible, even under challenging conditions. Data collection wasn't continuous for all sites. Some telescopes faced brief interruptions due to weather, mechanical issues, or other factors. The global network's redundancy allowed the team to compensate, with other observatories filling in gaps during these periods. As the Earth rotated, the alignment of telescopes relative to M87* changed. This movement created a wider array of observational baselines, effectively increasing the resolution of the virtual telescope. Each additional angle contributed to a sharper final image. Night after night, the hard drives at each site filled with raw data. These drives were carefully stored and transported to processing centers. Every observation had to be meticulously documented, ensuring that no data was lost or misaligned. The team used precise scheduling to maximize the available time for each telescope. Every minute counted, as M87* could only be observed during specific windows when it was visible in the sky. Coordination across the network ensured that these windows were fully utilized. The accumulation of data over multiple nights allowed the team to account for fluctuations in the environment. By averaging observations and cross-referencing signals, they could filter out noise and isolate the true emissions from the black hole's vicinity. This method increased the reliability of the final image. Each night of observation brought new challenges and new opportunities. The process was a careful balance of technical expertise, patience, and adaptability. Over these nights, the team built the foundation for one of the most significant achievements in modern astronomy. Transforming the raw data from the Event Horizon Telescope into a coherent image relied on advanced computational techniques. These methods allowed scientists to process the enormous data sets and reconstruct the shadow of M87*. Without these tools, the faint signals would have remained unintelligible. One of the most important techniques used was very long baseline interferometry, or VLBI. This process combined data from telescopes across the globe to simulate the resolving power of a single Earth-sized telescope. By correlating signals from each site, VLBI created a unified dataset. The data from each telescope needed to be perfectly aligned. Atomic clock timestamps ensured precise synchronization, but small differences still had to be corrected. Algorithms were developed to adjust for these variations, ensuring the signals matched exactly. Noise in the data posed another challenge. Background radiation, atmospheric interference, and instrumental noise all affected the raw signals. Filtering techniques were applied to isolate the true emissions from the black hole, preserving only the most reliable information. The gaps in the data collected over multiple nights required interpolation. Advanced algorithms filled in missing details by modeling the expected behavior of light and matter around the black hole. These models were based on simulations and theoretical predictions. Imaging techniques like the clean algorithm and the maximum entropy method played key roles in reconstructing the final image. These methods processed the correlated data to create a visual representation of the black hole's shadow. Each technique contributed to refining the image. Simulations provided a critical framework for validating the data. By comparing real observations to simulated models, scientists could test whether their techniques were accurate. These comparisons ensured the final image aligned with theoretical expectations. The computational process required enormous processing power. Supercomputers handled the billions of calculations needed to align, filter, and combine the data. These machines worked continuously for months to complete the analysis. Parallel processing allowed multiple stages of computation to happen simultaneously. This approach saved time and allowed the team to explore different imaging techniques. Each iteration improved the clarity and accuracy of the resulting image. Data calibration was another essential step. Small discrepancies between telescopes, such as differences in sensitivity, had to be corrected. Calibration tools ensured that the data from all sites was harmonized before it was combined. The iterative nature of the process required constant refinement. Scientists ran the data through various algorithms multiple times, each pass improving the image. This repetition helped remove artifacts and confirmed the reliability of the final result. The computational techniques developed for this project have applications beyond imaging black holes. They are now being used in other areas of astronomy and physics, from studying galaxy formation to analyzing gravitational waves. These innovations are a testament to the power of collaboration between technology and science. Generating the first image of a black hole required specialized algorithms to process and reconstruct the data. These algorithms were designed to handle incomplete, noisy signals and turn them into a coherent representation of M87*. Each step of the process relied on computational precision and innovation. One of the primary algorithms used was the CLEAN algorithm, originally developed for radio astronomy. CLEAN removed artifacts caused by the limited number of telescopes, refining the raw data and creating a clearer image. It worked iteratively, removing distortions and isolating the true signal. The maximum entropy method, or MEM, was another critical tool. MEM focused on filling gaps in the data by maximizing the smoothness and consistency of the reconstructed image. It was particularly useful for ensuring that the final result matched the expected structure of a black hole's shadow. Fourier transforms were used to convert the raw data into a form that could be analyzed spatially. This mathematical process allowed the team to study the intensity and distribution of the signals, laying the foundation for building the image. It translated radio signals into visual patterns. Gradient descent methods optimized the image reconstruction process. These algorithms adjusted the parameters of the models step by step, minimizing errors and improving accuracy. They ensured that the image was both sharp and scientifically valid. Interferometry-specific algorithms correlated data from multiple telescopes. By analyzing the phase and amplitude of signals received at different locations, these tools combined the observations into a single dataset. This step was crucial for achieving the resolution needed to see the black hole's shadow. Wavelet transforms helped isolate features in the data across different scales. These transforms identified patterns that corresponded to the black hole's emissions, while filtering out noise. They enhanced the clarity of the final image by preserving key details. Machine learning played a role in testing and validating the algorithms. Neural networks trained on simulations helped identify errors and refine the reconstruction process. This approach ensured that the algorithms produced consistent and reliable results. The use of regularization techniques added stability to the image generation. These methods controlled how the algorithms handled uncertainties, preventing overfitting or unrealistic outputs. They balanced the need for detail with the requirement for accuracy. Data weighting algorithms prioritize signals based on their reliability. Observations with clearer paths and less interference were given more influence in the reconstruction process. This approach helped mitigate the impact of noise and missing data. Custom-designed algorithms were developed specifically for the Event Horizon Telescope. These tools combined elements of existing methods while addressing the unique challenges of imaging a black hole. They represented a fusion of traditional techniques and cutting-edge innovation. Iterative refinement processes allowed scientists to test multiple versions of the image. By comparing outputs from different algorithms, they could identify common features and eliminate artifacts. This cross-checking built confidence in the final image's accuracy. The algorithms used for this project pushed the boundaries of what is possible in computational imaging. They demonstrated the power of mathematics and technology to reveal phenomena that had previously been beyond human reach. Each one was a step toward capturing the shadow of a black hole. Machine learning and simulations played a crucial role in creating the first image of a black hole. These tools provided a way to test and validate the massive amounts of data collected by the Event Horizon Telescope. They helped scientists refine their methods and ensure the accuracy of the final image. Simulations created theoretical models of what M87*'s shadow should look like, based on Einstein's general relativity. These models were used as a reference, comparing real data to the predicted structure of a black hole. They acted as a guide for processing and reconstructing the observations. Machine learning was used to identify patterns within the noisy and incomplete data. Algorithms trained on simulated datasets were able to recognize the key features of the black hole's emissions. This capability helped distinguish meaningful signals from interference. Neural networks, a type of machine learning, were employed to handle the vast complexity of the data. These networks analyzed relationships between signals collected from different telescopes, finding connections that traditional methods might have missed. They provided an additional layer of confidence in the image reconstruction. Simulations tested how light bends and interacts around a black hole. These tests incorporated factors like the spin, mass, and orientation of M87*. By replicating the conditions near the event horizon, simulations helped scientists refine their understanding of the data. Machine learning helped optimize the parameters of the algorithms used to generate the image. It identified the best configurations for filtering noise, filling gaps, and correlating signals. This automation streamlined the process, allowing scientists to focus on interpreting the results. The combination of simulations and machine learning provided a way to cross-check results. By running the data through multiple approaches, scientists could compare outputs and confirm consistent features. This redundancy reduced the likelihood of errors or false patterns. Simulations also explored how different types of noise or interference would impact the data. By understanding these effects, the team could develop better corrections during processing. This proactive approach ensured that even faint signals were preserved. Machine learning tools were used not only during image reconstruction, but also in identifying ideal observation conditions. They analyzed past datasets to predict when and how the telescopes should be used for the clearest possible results. This planning increased the efficiency of the observations. The insights gained from simulations extended beyond M87*. They helped refine models of black hole behavior, influencing future research across astrophysics. The success of these tools demonstrated the growing importance of computational techniques in modern science. The application of machine learning required collaboration between astronomers and computer scientists. Each discipline contributed its expertise to develop tools that could handle the unique challenges of the project. This interdisciplinary approach was key to overcoming the technical obstacles. Simulations and machine learning were not just supplementary, they were integral to the success of the Event Horizon Telescope. They bridged the gap between theory and observation, transforming raw data into a groundbreaking image. Together, these tools revealed the shadow of a black hole for the first time. Refining the image of M87* was a meticulous process that involved multiple stages of analysis and adjustment. The raw data collected by the Event Horizon Telescope had to be carefully processed to remove noise and align signals. Each step was critical to revealing the faint shadow of the black hole. The first step in refinement was calibrating the data from each telescope. Differences in sensitivity, weather conditions, and equipment needed to be accounted for to ensure consistency. Calibration tools adjusted for these variables, creating a uniform dataset for further analysis. Noise reduction was one of the biggest challenges. Signals from M87* were faint and easily masked by interference from cosmic and terrestrial sources. Advanced filtering techniques were applied to isolate the true emissions from the black hole, preserving only the most reliable information. Multiple algorithms were used to reconstruct the image from the processed data. Each algorithm provided a slightly different perspective, highlighting various features of the black hole's shadow. Comparing these outputs helped refine the image and confirm its accuracy. Cross-validation was a key part of the refinement process. By running the data through different imaging techniques, scientists could identify consistent patterns that appeared across all methods. This approach ensured that the final image was not the result of any single algorithm's bias. Simulations were used to compare the real data to theoretical predictions. These models of how light bends and behaves near a black hole acted as a reference, guiding adjustments to the reconstructed image. The closer the data matched the simulations, the more confidence the team had in its accuracy. Iterative improvement played a major role in the refinement process. Scientists revisited the data multiple times, each pass fine-tuning the image. This repetition allowed them to catch subtle details and remove artifacts that might have been overlooked initially. Collaborative input from teams around the world further enhanced the refinement. Scientists from different disciplines and institutions reviewed the image and provided feedback. This diversity of expertise ensured that every aspect of the data was thoroughly examined. Redundant checks were built into every stage of the process. Independent teams worked on parallel versions of the image, comparing results to identify and eliminate errors. This redundancy was vital for achieving a trustworthy final image. Visualizing the data involved balancing detail with clarity. Too much focus on specific features could obscure the overall structure, while too little detail risked losing important information. Refinement techniques aimed to strike the perfect balance, preserving the integrity of the shadow. Combining multiple nights of observations added another layer of refinement. By averaging data from different time periods, the team reduced the impact of temporary noise or fluctuations. This method ensured that the final image represented a consistent and stable view of M87*. The refinement process turned raw signals into the historic image of M87*. Every adjustment, comparison, and validation brought the team closer to capturing the true nature of the black hole's shadow. It was a culmination of expertise, innovation, and relentless attention to detail. The first image of a black hole revealed a dark, circular shadow surrounded by a bright, glowing ring. This shadow represents the event horizon, the boundary beyond which nothing can escape. The ring is light emitted by the hot gas swirling around the black hole, bent by its immense gravity. The shadow itself is not a physical structure but the absence of light. It is formed as the black hole's gravity traps everything within its grasp, including photons. Its nearly circular shape confirmed predictions based on Einstein's theory of general relativity. The glowing ring is the result of intense radiation emitted by the black hole's accretion disk. This disk consists of gas and dust heated to millions of degrees as it spirals inward. The brightness varies around the ring, a result of the black hole's rotation and the relativistic effects near the event horizon. The image captures light distorted by gravitational lensing. The black hole's gravity bends the light emitted by the accretion disk, creating the appearance of a ring. This bending also allows us to see areas of the disk that would otherwise be hidden from view. The asymmetry in the brightness of the ring provides key information about the black hole's spin. The brighter region corresponds to material moving toward us, its light boosted by relativistic beaming. The dimmer side indicates material moving away. The dark region in the center, the shadow, measures about 40 billion kilometers across. Despite its immense size, its distance of 55 million light-years makes it appear tiny in the sky. The Event Horizon Telescope achieved the incredible resolution necessary to capture this shadow. This image is a composite created from data collected by telescopes around the world. It represents an average of the signals received during multiple nights of observation. The team used advanced algorithms to reconstruct the shadow and its surrounding features. The ring's thickness and structure reveal details about the black hole's environment. It shows how matter interacts with the intense gravitational and magnetic fields near the event horizon. These interactions produce the energy that powers the bright emissions. The color of the image is not real but represents the intensity of radiation detected by the telescopes. Scientists chose a color scale to highlight the contrast between the bright ring and the dark shadow. This choice helps to visually emphasize the black hole's defining features. The precision of the image was remarkable, matching theoretical predictions with stunning accuracy. The nearly perfect circularity of the shadow provided strong evidence supporting general relativity. Any significant deviations would have challenged our understanding of gravity. This first image of M87* is more than a photograph. It is a map of extreme physics. It shows how light and matter behave in one of the most hostile environments in the universe. Every detail offers new insights into the nature of black holes and spacetime. The image was a historic achievement, providing humanity's first direct view of a black hole's shadow. It confirmed decades of theory and opened new pathways for exploring the mysteries of the universe. This was our first glimpse into the heart of one of nature's most enigmatic objects. The silhouette of the black hole is defined by the shadow at its center, encircled by a glowing ring. This shadow is the region where light is absorbed by the event horizon, creating a stark contrast against the surrounding emissions. It's the first visual evidence of a black hole's presence. The nearly circular shape of the shadow confirms the immense gravitational pull of the black hole. This shape is a direct result of how space-time is warped around such a massive object. It matches the theoretical predictions made using general relativity. The bright ring surrounding the shadow is formed by photons that narrowly escape the black hole's gravity. These photons originate from the accretion disk, a swirling collection of hot gas and dust. The bending of light by gravity makes the ring appear to wrap completely around the black hole. Variations in the brightness of the ring are one of its key features. The brighter regions indicate areas where material in the accretion disk is moving toward us, boosting the light through relativistic effects. The dimmer regions correspond to material moving away. The thickness of the ring provides clues about the black hole's environment. It reflects the density and energy of the matter in the accretion disk. A thinner or uneven ring could indicate variations in the flow of material being pulled inward. The size of the shadow is proportional to the black hole's mass. In the case of M87*, the shadow spans a distance of 40 billion kilometers, corresponding to its 6.5 billion solar mass black hole. This size confirms its status as one of the largest known black holes. The dark interior of the silhouette is not completely devoid of light. Some light paths are bent and scattered within the event horizon, but they never escape to reach observers. This creates the appearance of an all-encompassing darkness at the center. The glowing ring also reveals the presence of magnetic fields around the black hole. These fields influence how material moves within the accretion disk and how energy is emitted. The interplay between these forces shapes the overall structure of the silhouette. Gravitational lensing, caused by the black hole's intense gravity, distorts the light from the accretion disk. This effect allows us to see parts of the disk that lie behind the black hole. The silhouette is not only a shadow, but a visual representation of space-time bending. The silhouette's symmetry reflects the alignment of the black hole's spin axis with our line of sight. Slight asymmetries in the ring may provide information about the black hole's orientation and rotation speed. These details help us understand the black hole's dynamics. The features of the silhouette also hint at the properties of the black hole's event horizon. The sharp boundary of the shadow marks the limit where light can no longer escape. This is the defining edge of the black hole, shaping its visual presence. Each feature of the silhouette is a window into the extreme physics of the black hole. From the brightness of the ring to the depth of the shadow, every detail tells a story about the forces at play. The silhouette is not just an image but a map of one of the universe's most mysterious regions. The reaction from the scientific community was immediate and profound. The first image of a black hole was hailed as a groundbreaking achievement, confirming decades of theoretical predictions. It represented a milestone not only for astrophysics but for science as a whole. Physicists and astronomers praised the image as a validation of Einstein's theory of general relativity. The nearly perfect circular shadow aligned closely with the predictions made over a century ago. This result reaffirmed the theory's robustness under extreme conditions. The collaborative effort behind the image was equally celebrated. Scientists across the globe marveled at the success of the Event Horizon Telescope project. It demonstrated the power of international cooperation and the shared pursuit of knowledge. Many researchers were struck by the precision of the observations. Achieving such clarity at a distance of 55 million light-years was seen as a testament to the advancements in technology and computational methods. It set a new standard for what is possible in observational astronomy. The image sparked excitement among theorists studying black holes. It provided direct visual evidence to test models of accretion disks, jets, and gravitational lensing. The data offered a treasure trove of opportunities for refining existing theories. Astrophysicists were particularly intrigued by the variations in the ring's brightness. These asymmetries suggested details about the black hole's spin and the motion of surrounding material. It opened new avenues for understanding the dynamics of these massive objects. Scientists working in related fields, from cosmology to quantum mechanics, saw implications for their own research. The black hole's extreme environment offers a unique laboratory for studying fundamental forces. The image has the potential to bridge gaps between different areas of physics. The reaction extended beyond academic circles. Universities and institutions organized lectures and discussions to dissect the findings. For many researchers, the image became a focal point for exploring the broader mysteries of the universe. Journals and conferences featured the image prominently, showcasing it as a defining moment in modern science. Papers analyzing the data were quickly published, with researchers eager to share their insights. The scientific discourse around the black hole grew rapidly. The success of the project inspired confidence in future endeavors. Scientists began discussing the next steps for imaging other black holes, such as Sagittarius A** at the center of the Milky Way. The Event Horizon Telescope demonstrated that these challenges could be overcome. The image also highlighted the value of interdisciplinary collaboration. From engineers designing hardware to computer scientists developing algorithms, experts from diverse fields contributed to the achievement. The project showed how combining expertise can lead to extraordinary results. The scientific community's reaction underscored the significance of this discovery. The first image of a black hole was more than a technical achievement. It was a moment of collective triumph. It united scientists worldwide in awe and appreciation of what humanity can achieve through curiosity and determination. The release of the first black hole image captured the imagination of the world. News outlets across the globe featured it prominently, with headlines celebrating the groundbreaking achievement. The image quickly became a symbol of humanity's ability to uncover the universe's deepest mysteries. Social media platforms were flooded with reactions, as people marveled at seeing something that had only existed in theory. The glowing ring and dark shadow sparked curiosity and wonder, inspiring discussions about science and space exploration. It became a viral moment that transcended cultural and geographic boundaries. Public interest in black holes surged, with many seeking to understand the science behind the image. Educational institutions reported increased attendance at lectures and workshops on astrophysics. The image provided a rare opportunity to engage people in complex scientific concepts. The historic nature of the achievement was widely recognized. The black hole image was compared to iconic moments in science, such as the Apollo moon landing. It became a defining visual of our era, representing the triumph of collaboration and technology. Artists and creators were inspired by the black hole's haunting beauty. The image was reimagined in paintings, music, and digital art, blending science with culture. It became a muse for those exploring themes of the unknown and the infinite. Many saw the image as a reminder of humanity's shared potential. The global effort to capture the black hole resonated with people from all walks of life. It symbolized what can be achieved when we unite to pursue knowledge and push the boundaries of what is possible. Media outlets emphasized the international nature of the Event Horizon Telescope collaboration. Stories highlighted the contributions of scientists from diverse backgrounds, showcasing the project as a model of global cooperation. It was a moment that celebrated the universality of science. The scientific team behind the image became instant celebrities. Researchers, engineers, and project leaders were interviewed extensively, sharing their insights and experiences. Their stories added a human element to the monumental achievement, making the science more accessible. Documentaries and feature stories delved into the technology and effort behind the image. Audiences were fascinated by the intricate details of how the telescopes operated and how the data was processed. These narratives turned the technical achievement into a compelling tale of discovery. Children and students were particularly captivated, with many expressing newfound interest in space and science. The black hole image was used in classrooms to spark curiosity and encourage exploration. It became an educational tool that inspired the next generation of scientists and thinkers. The public response demonstrated a deep appreciation for the mysteries of the universe. People from all backgrounds found meaning and inspiration in the image, connecting it to questions about existence and our place in the cosmos. It reminded many of the importance of scientific exploration. The media and public reaction solidified the black hole image as more than a scientific milestone. It became a cultural phenomenon, a moment of awe and celebration shared by millions. Its impact extended far beyond the scientific community, leaving an enduring legacy in the collective imagination. The first image of a black hole opened the door to a new era of observational astronomy. It demonstrated that capturing the shadow of a black hole is not only possible, but repeatable. This success set the stage for imaging other black holes and studying their unique properties. One immediate goal is to observe Sagittarius A*, the supermassive black hole at the center of our galaxy. Unlike M87*, Sagittarius A* is much smaller and more dynamic, making it a challenging but valuable target. Studying its shadow could provide insights into how black holes behave in different environments. The techniques developed for the Event Horizon Telescope can now be applied to other targets. By refining these methods, scientists aim to achieve even higher resolution and sensitivity. This will allow for more detailed studies of accretion disks, jets, and gravitational lensing effects. Future observations could focus on tracking changes in black holes over time. Monitoring the activity around event horizons could reveal how matter behaves as it falls inward. This dynamic view would add depth to our understanding of black hole physics. Expanding the Event Horizon Telescope network is another critical step. Adding more observatories, particularly in previously uncovered regions, would improve data quality and resolution. A larger network would enhance the ability to image smaller or more distant black holes. Polarized light studies are also a promising avenue. Polarization data can reveal the structure of magnetic fields near black holes, providing clues about how jets are formed. Understanding these fields is key to uncovering the mechanisms that power some of the universe's most energetic phenomena. Imaging black holes in different wavelengths of light could offer new perspectives. Observing in radio, infrared, or X-ray bands would capture additional details about their surroundings. Combining data from multiple wavelengths would create a more complete picture of these cosmic giants. The success of the first image inspires further exploration of black hole mergers. Detecting the shadows of merging black holes, along with gravitational waves, could offer unprecedented insights into these dramatic events. This combination of observations would bridge two powerful methods of studying the universe. The techniques used for black hole imaging also have broader applications. They could be adapted to study other compact objects, such as neutron stars, or to observe fine details in distant galaxies. These advancements will benefit multiple fields of astronomy. Continued observations may also help resolve fundamental questions about black holes. Investigating phenomena like Hawking radiation or quantum effects at the event horizon could shed light on the intersection of general relativity and quantum mechanics. These studies could reshape our understanding of the cosmos. Collaborations between observatories and missions in space could enhance future efforts. Space-based telescopes, free from atmospheric interference, could complement ground-based observations. Together, they would achieve unparalleled precision in black hole studies. The first image has set a high standard for what is possible in astronomy. It has sparked new ideas, new collaborations, and new ambitions for exploring the universe. Each future observation will build on this foundation, expanding our knowledge of black holes and the fundamental nature of reality. The first image of a black hole provided striking confirmation of Einstein's general theory of relativity. The nearly circular shadow and the bending of light around the black hole matched predictions made over a century ago. It was a powerful validation of one of the most fundamental theories in physics. General relativity describes how massive objects warp spacetime, creating the intense gravitational fields that define a black hole. The shadow observed in the image is a direct result of this warping, perfectly aligning with Einstein's equations. This agreement strengthened the theory's standing as the cornerstone of modern astrophysics. The bending of light, or gravitational lensing around the black hole, was another key prediction confirmed by the image. This effect allows us to see the glowing ring of the accretion disk, even parts that are behind the black hole. The observed structure mirrored the patterns predicted by relativity. The size of the shadow provided additional evidence. Based on the mass of M87*, general relativity predicted the diameter of the shadow with remarkable accuracy. The image confirmed this prediction, showcasing the precision of Einstein's theory even under extreme conditions. Relativistic beaming, visible in the brightness asymmetry of the ring, is another phenomenon explained by general relativity. The brighter side corresponds to material moving toward us, with its light boosted by the black hole's intense gravity and high velocities. This effect was clearly evident in the image. The confirmation of these effects solidified the idea that general relativity holds true in the most extreme environments. Black holes represent the ultimate test of the theory, where space-time is stretched and curved to its limits. The image proved that Einstein's ideas endure even in such extreme scenarios. The study of the black hole's event horizon offered further validation. Relativity predicts a sharp boundary where light and matter are trapped forever. The image captured this boundary as a defined shadow, perfectly consistent with the theory's expectations. Einstein's work also predicted the relationship between a black hole's mass and its gravitational influence. The image of M87* showed how accurately this relationship holds, with the observed shadow size correlating directly with the black hole's immense mass. It was a testament to the theory's robustness. Even the techniques used to create the image drew from relativity. Simulations and models based on Einstein's equations helped guide the reconstruction of the shadow. The image wasn't just evidence of relativity, it was built on its foundation. The success of the image encouraged scientists to explore deeper questions about relativity. While the theory passed this test, researchers are eager to push its boundaries further. Studying black holes like M87* may one day reveal where general relativity breaks down or how it connects with quantum mechanics. The image demonstrated not only the accuracy of Einstein's equations, but their predictive power. Long before black holes were directly observed, relativity described their properties with astonishing precision. The image of M87** brought those predictions into reality. Each feature of the image, from the shape of the shadow to the brightness of the ring, served as a confirmation of Einstein's vision. It was a moment of triumph for theoretical physics, showing that ideas conceived a century ago still describe the universe with breathtaking accuracy. The first image of a black hole offered profound insights into the physics of these mysterious objects. By directly observing the shadow and surrounding emissions, scientists gained a clearer understanding of how black holes interact with their environment. It provided a new perspective on the forces at play near an event horizon. The structure of the accretion disk revealed details about how matter behaves in extreme gravitational fields. The bright, glowing material spiraling into the black hole emits intense radiation, allowing scientists to study the properties of matter under immense pressure and heat. This offers clues about the physics of accretion and energy transfer. The asymmetry in the ring's brightness highlighted the effects of relativistic beaming. Matter moving toward us appeared brighter due to its high velocity and the black hole's gravitational influence. This confirmed how black holes accelerate and manipulate surrounding material. Magnetic fields near the black hole were indirectly observed through the image. The interplay between these fields and the accretion disk is crucial for understanding how jets are formed. These powerful outflows of energy and matter are key to studying black hole feedback on their galaxies. The size of the shadow provided a direct measurement of the black hole's mass. This calculation aligned with previous estimates based on the motion of stars and gas around M87*. It demonstrated the accuracy of using shadow size as a tool for determining black hole properties. The image also confirmed the existence of the photon sphere, where light orbits the black hole before escaping or being absorbed. Observing this sphere helps refine our understanding of how gravity bends light near an event horizon. It is a striking example of space-time curvature in action. Insights into the stability of the accretion disk were also gained. The smooth and well-defined ring suggested a relatively steady flow of material into the black hole. This stability provided an ideal opportunity to study the long-term behavior of accretion processes. The interaction between the black hole's spin and its accretion disk offers clues about its rotation rate. The orientation and brightness of the ring suggest how energy is extracted from the black hole's spin to power jets. Understanding this relationship is key to decoding black hole dynamics. The ability to study a supermassive black hole directly brings new opportunities to test alternative theories of gravity. While the image aligned with general relativity, it also serves as a baseline for exploring deviations predicted by other models. This could lead to discoveries beyond Einstein's framework. The data also informs our understanding of black hole entropy and thermodynamics. The event horizon acts as a thermodynamic boundary, with implications for the behavior of information and energy in extreme conditions. Observing the shadow brings these theoretical concepts closer to empirical study. The role of black holes in galactic evolution was reinforced by the image. The energy released by M87** influences star formation and the distribution of matter in its host galaxy. Observing this process helps bridge the gap between black hole physics and cosmology. Each detail captured in the image adds to the growing understanding of black hole physics. From the shadow's size to the ring's brightness, every feature is a window into the most extreme environments in the universe. It is a monumental step in unraveling the mysteries of black holes and their role in the cosmos. Accretion disks are one of the most fascinating features surrounding black holes. They form as gas and dust spiral inward, pulled by the black hole's immense gravity. The material in these disks becomes incredibly hot and emits intense radiation, making them some of the brightest objects in the universe. The image of M87** provided a unique view of its accretion disk. The glowing ring captured in the image is the radiation emitted by this spiraling material. Its structure and brightness offer critical clues about the processes occurring near the event horizon. The dynamics of the accretion disk are influenced by the black hole's spin and gravity. Material within the disk orbits at varying speeds, with inner regions moving faster than outer ones. This differential motion generates friction, heating the material to millions of degrees. The energy released in the accretion disk powers the emissions we observe. X-rays, radio waves, and other forms of radiation escape the disk, giving us a window into its behavior. These emissions also allow scientists to map the physical conditions within the disk. The disk's stability depends on the balance between the inward pull of gravity and the outward pressure of the hot gas. Observing this balance helps scientists understand how matter flows into the black hole. Stable disks, like the one around M87*, provide ideal conditions for such studies. Magnetic fields play a significant role in shaping the disk's behavior. These fields can create turbulence within the disk, influencing how material moves and clumps together. They also help launch jets of matter and energy away from the black hole. The thickness of an accretion disk varies depending on the black hole's activity. Thin disks, like the one observed around M87*, are often more stable and emit less turbulent radiation. Thicker disks can indicate more chaotic environments with higher rates of material falling inward. The interaction between the disk and the black hole's spin is a key area of research. The rotation of the black hole can drag space-time around it, affecting the motion of the disk. This phenomenon, known as frame dragging, is visible in the shape and brightness of the ring. Accretion disks also provide insights into the feeding habits of black holes. By observing the amount of material in the disk, scientists can estimate how much matter the black hole consumes. This helps explain the growth of supermassive black holes over time. The temperature of the disk influences the type of radiation it emits. Hotter disks produce high-energy emissions like X-rays, while cooler disks emit lower-energy radiation. This variation allows astronomers to study different regions of the disk across multiple wavelengths. Accretion disks are not just passive features, they actively shape their surroundings. The radiation and winds they produce can heat nearby gas and affect star formation. This feedback mechanism links the behavior of the disk to the evolution of the host galaxy. The first image of M87* provided an unprecedented look at an accretion disk in action. Every detail in the glowing ring revealed something about the forces at work near the event horizon. It was a vital step in understanding how black holes interact with the matter around them. The first image of a black hole had a transformative impact on astrophysics. It provided direct evidence of phenomena that had been studied only theoretically for decades. The image confirmed existing models while opening new paths for exploration and discovery. This achievement reinforced the role of general relativity in describing the universe. By validating predictions about the shape and size of the shadow, it solidified our understanding of how gravity operates under extreme conditions. It also set a new benchmark for testing alternative theories of gravity. The success of the Event Horizon Telescope demonstrated the power of global collaboration in tackling complex scientific problems. Astrophysics has always been an international effort, but this project took coordination to an unprecedented level. It highlighted the value of pooling expertise and resources. For observational astronomy, the image marked a leap forward in resolution and precision. It showed that it is possible to study objects as small as a black hole's event horizon across vast cosmic distances. This breakthrough has inspired new technological advancements in telescope design. The image also brought attention to the importance of multi-wavelength observations. By combining data from different parts of the electromagnetic spectrum, scientists gained a more complete picture of M87*. This approach is now being applied to other celestial phenomena. The data provided new insights into the behavior of matter and energy near a black hole. Observing the accretion disk and jets in such detail has deepened our understanding of the physics governing these regions. It has also shed light on the mechanisms that drive high-energy emissions. Astrophysicists have used the image to refine models of black hole growth and evolution. By studying the shadow and its surrounding features, they can better understand how supermassive black holes interact with their host galaxies. This has implications for theories about galaxy formation and evolution. The project highlighted the role of computational methods in modern astrophysics. Advanced algorithms and simulations were crucial for processing the data and reconstructing the image. These tools are now being used in other areas of research, from exoplanet studies to cosmology. The discovery has inspired renewed interest in gravitational wave astronomy. Combining observations of black holes with gravitational wave data could provide a more comprehensive understanding of their dynamics. This integrated approach promises to reveal new aspects of astrophysical phenomena. The image has also sparked a new generation of theoretical research. Scientists are exploring the implications of the shadow's features for concepts like black hole entropy, Hawking radiation, and quantum gravity. Each discovery pushes the boundaries of what we know. Education and public outreach have benefited significantly from the image's impact. It has made black holes and their physics more accessible to students and the general public. This visibility has encouraged greater interest in science and astronomy as fields of study. The first image of a black hole has become a cornerstone of astrophysics. It represents the culmination of decades of research, while setting the stage for future discoveries. Its impact will resonate across the field for years to come, shaping how we study and understand the universe. The first image of a black hole raised as many questions as it answered. While it confirmed long-standing theories, it also highlighted gaps in our understanding. Each new detail in the image pointed to deeper mysteries waiting to be explored. One major question concerns the nature of the event horizon itself. The sharp boundary observed aligns with general relativity, but it leaves unanswered questions about what happens to matter that crosses it. This leads to broader inquiries about the ultimate fate of information and energy. The role of magnetic fields near black holes is another area ripe for investigation. How these fields interact with the accretion disk and power jets remains only partially understood. Future observations may reveal the precise mechanisms behind these interactions. The spin of the black hole, inferred from the image, opens new questions about its formation and history. How did M87* acquire its immense angular momentum? And what does this tell us about the evolution of supermassive black holes? Understanding spin may unlock clues about their growth. The variability in the brightness of the accretion disk suggests dynamic processes at play. What causes these fluctuations, and how do they affect the matter falling into the black hole? Studying these changes over time could provide insights into the life cycle of active black holes. The shadow's size and shape were consistent with general relativity, but what if future observations reveal deviations? Such anomalies could point to new physics beyond Einstein's theory. This possibility motivates continued imaging of black holes under different conditions. The connection between black holes and their host galaxies raises additional questions. How do supermassive black holes influence star formation, and what role do they play in regulating galaxy evolution? M87* offers a unique opportunity to study these interactions. Jets like the one observed in M87 are among the most energetic phenomena in the universe. How exactly are these jets formed, and why do they vary in strength and direction? Understanding their origins is critical for unraveling the behavior of matter near black holes. The first image also highlights the need to study black holes of different sizes and types. How do the properties of smaller black holes compare to those of giants like M87*? Exploring this diversity could reveal commonalities and differences in their physics. The idea of quantum effects near the event horizon raises profound theoretical questions. Could subtle phenomena, undetectable in the first image, provide hints about the interplay between gravity and quantum mechanics? Observing these effects would bridge fundamental gaps in physics. The black hole's impact on the surrounding space-time suggests further exploration of gravitational waves. How do black hole mergers, captured by gravitational wave detectors, compare to static images like M87*? Combining these observations could provide a fuller picture of their dynamics. Finally, the shadow itself remains a symbol of the unknown. What lies beyond our current ability to observe, and how will future technologies expand this frontier? The first image is just the beginning, inspiring a cascade of questions that will shape the next era of discovery. The Event Horizon Telescope project was a truly global endeavor, involving countries and institutions from around the world. Scientists and engineers from over 20 nations contributed their expertise, resources, and technology to make the first black hole image possible. This international collaboration showcased the shared commitment to advancing our understanding of the universe. The United States played a leading role, with institutions like the National Science Foundation providing critical funding. Observatories such as those in Arizona and Hawaii formed key components of the telescope network, capturing essential data from their unique locations. Europe contributed significantly through organizations like the European Southern Observatory. Facilities in Spain and Greenland provided important vantage points for observing M87*. European teams were also instrumental in developing the algorithms used for data processing. Japan's involvement included contributions from the National Astronomical Observatory of Japan and telescopes such as ALMA in Chile, where Japanese technology enhanced data collection. Japanese researchers brought expertise in both instrumentation and analysis. Chile's high-altitude observatories played a pivotal role in the project. The Atacama Large Millimeter Submillimeter Array, or ALMA, provided some of the most sensitive data. Its location in the Andes ensured clear observations free from much atmospheric interference. Antarctica was home to another vital component of the network. The South Pole Telescope offered a unique perspective, its position allowing for continuous observations during the Southern Hemisphere's winter. This station extended the global coverage of the array. Institutions in Mexico, including the Large Millimeter Telescope, contributed data from a strategically important geographic location. Positioned in the Northern Hemisphere, this observatory helped fill gaps in the network's coverage. Collaboration in East Asia included efforts from China, Taiwan, and South Korea. These nations provided technological expertise and critical observational support, strengthening the global network. Their involvement underscored the truly international nature of the project. Canada and Australia were also key contributors, offering expertise in data analysis and algorithm development. Their scientists worked alongside other international teams, ensuring the data was processed with precision and care. Partnerships with institutions in Africa and the Middle East expanded the reach of the project. While these regions had fewer telescopes in operation, they contributed valuable resources and future development plans to enhance global capabilities. Each participating country brought unique strengths to the table, whether in engineering, funding, or theoretical research. This diversity of skills and perspectives was essential for overcoming the challenges of imaging a black hole. It demonstrated how science transcends borders. The Event Horizon Telescope was not just a scientific success, but a diplomatic one. It united countries with different histories, cultures, and priorities in a shared pursuit of discovery. The collaboration serves as a model for future global scientific efforts. Teamwork and coordination were the foundation of the Event Horizon Telescope's success. With hundreds of scientists and engineers involved across continents, collaboration was essential to achieving a single unified goal. Every step of the process depended on effective communication and shared expertise. The project required tight synchronization among observatories in vastly different locations. Teams had to align their schedules to conduct simultaneous observations of M87*. This coordination ensured that each telescope's data could be combined seamlessly with the rest. Scientists from diverse backgrounds worked together, blending expertise in astronomy, engineering, and computer science. Each discipline brought unique skills to the table, allowing the project to address its many technical and theoretical challenges. The diversity of knowledge was one of its greatest strengths. Regular meetings and discussions kept the teams connected despite being spread across different time zones. These interactions allowed researchers to share updates, troubleshoot problems, and refine their methods in real time. The constant flow of communication was vital to the project's progress. Coordinating such a large group required clear leadership and defined roles. Project managers ensured that every participant understood their responsibilities and how their work fit into the bigger picture. This structure helped maintain focus and avoid unnecessary duplication of efforts. Trust and collaboration were at the heart of the team's dynamic. Each observatory relied on the others to deliver high-quality data, knowing that the project's success depended on everyone's contributions. This sense of mutual reliance fostered a spirit of camaraderie. Even the data processing stage required a global effort. After observations were complete, teams worked together to analyze the vast amounts of information collected. Different groups focused on specific aspects, such as calibration, imaging, and validation, ensuring no detail was overlooked. The technical challenges of combining data from telescopes worldwide demanded close cooperation. Engineers and scientists worked hand in hand to synchronize the equipment, align the signals, and refine the algorithms used for image reconstruction. Their teamwork transformed raw signals into a coherent image. The collaboration extended to sharing resources and knowledge. Institutions with advanced facilities supported those with fewer capabilities, ensuring that every team could contribute effectively. This pooling of resources highlighted the project's commitment to inclusivity and shared success. Language and cultural differences added complexity, but were embraced as opportunities for learning. Scientists from different countries adapted to one another's communication styles, creating a unified team despite their diverse backgrounds. This global unity was a defining feature of the project. Even when setbacks occurred, the team's coordination allowed them to adapt quickly. Whether facing weather delays, technical issues, or data discrepancies, the participants worked together to find solutions. Their ability to remain flexible and resilient was crucial to overcoming challenges. The role of teamwork in the Event Horizon Telescope cannot be overstated. It showed how collaboration across disciplines, countries, and cultures can achieve the seemingly impossible. The project stands as a testament to what can be accomplished when humanity works together toward a common goal. The success of the Event Horizon Telescope was driven by a group of visionary leaders and key figures. These individuals brought their expertise, dedication, and innovative thinking to guide the project through its challenges. Their leadership was instrumental in turning an ambitious idea into a historic achievement. Shepard Dolman, the director of the Event Horizon Telescope, played a central role in organizing the global collaboration. His vision for linking telescopes across the world created the foundation for the project. Under his leadership, the team transformed a bold concept into reality. Katie Booman became one of the most recognized figures for her work on the imaging algorithms. Her contributions to developing methods for reconstructing the black hole's shadow were critical to the final image. Booman's work exemplified the innovative thinking needed to overcome the project's challenges. Heino Falke, a theoretical astrophysicist, contributed significantly to the scientific framework behind the observations. He was among the first to propose capturing an image of a black hole's shadow. His early advocacy and theoretical insights helped shape the project's goals. Daniel Morona, an astronomer specializing in radio observations, coordinated efforts between observatories. His expertise ensured that the telescopes in the network operated in harmony, collecting data precisely as planned. Morone's role was key to achieving the synchronization required for success. Avery Broderick, a theoretical physicist, worked on interpreting the data from M87*. His focus on the physics of accretion disks and relativistic effects helped translate the observations into meaningful scientific insights. Broderick's analysis added depth to the project's findings. Vincent Fish, a scientist with expertise in interferometry, contributed to the development of techniques for combining signals from multiple telescopes. His work ensured that the data could be aligned and correlated to produce the image. Fish's technical knowledge was indispensable. Chi-Kwan Chan, a computational astrophysicist, worked on simulations and data processing. His efforts helped test the imaging algorithms and verify the results. Chan's work bridged the gap between theoretical predictions and observational data. Lindy Blackburn, an expert in data calibration, was instrumental in refining the raw signals collected by the telescopes. His role involved ensuring the accuracy and consistency of the data before it was processed into an image. Blackburn's meticulous work laid the groundwork for the final results. Radboud University and the Max Planck Institute for Radio Astronomy were among the institutions that provided leadership in both research and resources. Their support and involvement underscored the importance of institutional collaboration in such a large-scale project. Teams from MIT's Haystack Observatory and Harvard's Black Hole Initiative provided crucial technical and theoretical contributions. These institutions were at the forefront of developing the tools and models that made the image possible. Their involvement highlighted the importance of academic partnerships. Each key figure and leader brought a unique perspective and expertise to the project. Together, they tackled the technical, scientific, and logistical challenges with remarkable determination. Their collective efforts turned the vision of imaging a black hole into a reality. The leadership within the Event Horizon Telescope project was a testament to the power of teamwork and innovation. It showed how individuals with different skills and backgrounds could come together to achieve something extraordinary. Their contributions will inspire future generations of scientists and engineers. The Event Horizon Telescope inspired international unity by demonstrating the power of global collaboration. It brought together scientists, engineers, and institutions from over 20 countries, united by the shared goal of capturing the first image of a black hole. This collective effort showcased what humanity can achieve when we work together. The project transcended borders. connecting observatories across continents. From the high-altitude deserts of Chile to the icy expanse of Antarctica, each location played a vital role. The network of telescopes became a symbol of global cooperation, each site contributing its unique perspective. This unity extended beyond science, fostering a sense of shared purpose among people from diverse backgrounds. Researchers overcame language barriers, cultural differences, and time zones to synchronize their efforts. Their collaboration highlighted the universal nature of curiosity and exploration. The EHT demonstrated how scientific discovery can bring nations together. Institutions from countries with different histories and priorities worked side by side. This collaboration set an example of how partnerships can thrive despite political or economic differences. The project's success was rooted in mutual trust and respect. Each team relied on the others to collect, process, and analyze data accurately. This interdependence created a strong bond, reinforcing the idea that progress is a collective achievement. Public reaction to the EHT underscored its role in uniting people worldwide. The image of M87* was celebrated across cultures, sparking wonder and excitement. It became a moment of shared inspiration, reminding humanity of our common pursuit of knowledge. The EHT also highlighted the importance of shared resources. Funding, expertise, and technology were pooled from institutions and governments around the globe. This model of resource sharing ensured that the project could achieve its ambitious goals. Educational outreach tied to the project further amplified its unifying impact. Lectures, documentaries, and social media campaigns reached audiences worldwide. The EHT became a platform for connecting people through science, inspiring students and citizens alike. The collaboration showed that science thrives on diversity. Teams with different skills and perspectives brought innovative solutions to complex challenges. This diversity of thought enriched the project and underscored the value of inclusion in scientific endeavors. The EHT's success encouraged future international collaborations. It proved that large-scale scientific challenges can be overcome through coordinated global efforts. This legacy will influence upcoming projects, from studying other black holes to exploring distant galaxies. The unity displayed by the EHT was a reminder of humanity's potential to overcome divisions. It showed that science can serve as a bridge, connecting people through the shared quest to understand the universe. This spirit of collaboration is a model for addressing challenges beyond astronomy. The Event Horizon Telescope was not just a scientific milestone, it was a triumph of global teamwork. It inspired hope and demonstrated the strength of unity, proving that when we come together, we can achieve the extraordinary. This message resonates far beyond the boundaries of science. The Event Horizon Telescope project required significant funding and careful resource allocation to succeed. Support came from a wide range of sources, including government agencies, research institutions, and international organizations. These contributions ensured that the project could meet its ambitious goals. The National Science Foundation in the United States was one of the largest supporters, providing crucial financial backing. Its funding covered the construction, operation, and maintenance of key observatories within the network. This support laid the foundation for the project's technical achievements. European funding agencies also played a major role, with contributions from organizations like the European Research Council. These resources helped upgrade observatories, enhance data processing facilities, and support the teams working on algorithm development. European institutions were integral to the project's success. Individual observatories received targeted funding to improve their capabilities. Investments were made in high-precision equipment, such as atomic clocks and sensitive receivers, which were essential for capturing the faint signals from M87*. These upgrades enabled the telescopes to function as part of the global network. Private organizations and foundations contributed as well, recognizing the historic nature of the project. Their support helped cover costs associated with logistics, outreach, and specialized equipment. This combination of public and private funding demonstrated the broad appeal of the scientific endeavor. Resource allocation within the project was carefully managed to maximize efficiency. Each observatory focused on its strengths, whether in data collection, processing, or calibration. This specialization ensured that the limited resources were used effectively and without duplication of effort. The transport and storage of data represented a significant logistical cost. Shipping massive amounts of information on hard drives required coordination and funding. Processing centers were equipped with state-of-the-art infrastructure, supported by dedicated financial resources. Human resources were another critical area of investment. The project supported hundreds of researchers, engineers, and technicians worldwide. Funding covered salaries, travel, and training, enabling the team to focus entirely on their work without external distractions. Outreach and education efforts also received funding, amplifying the project's impact beyond the scientific community. Public engagement programs, documentaries, and lectures brought the story of the Event Horizon Telescope to a global audience. These initiatives highlighted the importance of sharing discoveries with the world. Collaboration required the allocation of resources for communication and coordination. Virtual meetings, workshops, and conferences were supported to keep the international team connected. These efforts ensured that the project progressed smoothly despite its global scope. Balancing funding priorities was a constant challenge. The team had to allocate resources between immediate technical needs and long-term goals, such as preparing for future black hole observations. This careful planning ensured the project's sustainability and adaptability. The funding and resource allocation behind the Event Horizon Telescope reflected the shared commitment of nations, organizations, and individuals. It demonstrated how collective investment in science can lead to groundbreaking discoveries. This model will serve as a blueprint for future large-scale research endeavors. The first image of a black hole quickly became a cultural milestone, transcending its scientific significance. It captured the public's imagination, symbolizing humanity's ability to uncover the deepest mysteries of the universe. The glowing ring and shadow became icons of exploration and discovery. This image resonated with people from all walks of life, inspiring wonder and curiosity. It was more than a scientific achievement. It was a moment of collective awe. It reminded us of the beauty and vastness of the cosmos, sparking conversations far beyond the scientific community. Artists and creators found inspiration in the black hole's haunting silhouette. Paintings, music, and digital art emerged as expressions of this monumental discovery. The image became a bridge between science and the arts, showing how deeply space exploration touches human creativity. For educators, the black hole image became a powerful tool to engage students. It simplified complex concepts, making astrophysics accessible and exciting. Classrooms worldwide used the image to spark discussions about gravity, relativity, and the scale of the universe. The image was widely shared on social media, where it reached millions within hours of its release. Memes, discussions, and educational posts flooded timelines, bringing science into everyday conversations. This digital momentum helped make the discovery a truly global event. It also became a symbol of perseverance and collaboration. The years of effort and the teamwork behind the image were celebrated as much as the discovery itself. It showed what could be achieved when nations and disciplines come together to tackle a common challenge. The black hole's shadow sparked philosophical reflections about our place in the universe. For many, it was a humbling reminder of the vast unknown and humanity's small but significant role in exploring it. The image invited people to ponder questions about existence and reality. Culturally, the black hole image broke barriers between science and society. It appeared on magazine covers, in films, and even in fashion. Its reach extended beyond the academic sphere, becoming a symbol of curiosity and the pursuit of knowledge. The image also served as a unifying moment for humanity. In a world often divided, this glimpse of a distant black hole brought people together. It was a rare event that sparked collective pride and excitement on a global scale. This milestone highlighted the importance of making scientific achievements accessible. By sharing the image widely and explaining its significance, the Event Horizon Telescope team ensured that everyone could celebrate the discovery. It became a shared triumph for all of humanity. As a cultural milestone, the image stands alongside other great achievements in space exploration. Like the first photograph of Earth from space or the Apollo moon landing, it represents a leap in human understanding. Its impact will be remembered for generations. The first image of a black hole was more than a scientific accomplishment. It was a cultural moment. It connected people to the mysteries of the universe, inspiring wonder, creativity, and unity. Its legacy will continue to inspire future generations to reach for the stars. Black holes have long been a source of fascination in popular media, captivating audiences with their mystery and power. From science fiction films to novels, they are often portrayed as gateways to the unknown, symbols of cosmic danger, or portals to other dimensions. Their enigmatic nature makes them a perfect backdrop for storytelling. Movies like Interstellar brought black holes to mainstream attention with visually stunning and scientifically informed depictions. The film's portrayal of a supermassive black hole, based on accurate simulations, sparked widespread interest in astrophysics. It bridged the gap between science and entertainment, inspiring curiosity about the real phenomena. In literature, black holes are often used to explore themes of time, space, and existence. Writers have woven them into stories as metaphors for the infinite, or as settings for dramatic exploration. These narratives reflect humanity's fascination with the unknown and our quest to understand it. Television shows, particularly in the science fiction genre, frequently feature black holes as dramatic plot devices. They are depicted as both threats and opportunities, challenging characters to confront the limits of their knowledge. This duality mirrors the real scientific intrigue surrounding these objects. Video games have embraced black holes as a visual and conceptual element, using them to create immersive, otherworldly experiences. Players are often drawn into their gravitational pull, navigating challenges that echo the complexities of real astrophysics. These interactive depictions bring the wonder of black holes to new audiences. Documentaries and educational programming have played a vital role in demystifying black holes. They use visuals, expert commentary, and accessible explanations to present these phenomena to the public. Programs featuring black holes consistently capture high viewer interest, reflecting their universal appeal. Black holes have also found a place in music and art, inspiring compositions and creations that capture their mystery. From songs that reference their infinite nature to abstract artworks, they serve as a muse for exploring themes of scale, power, and the unknown. They resonate as symbols of both destruction and creation. Social media has amplified black holes' presence in popular culture. The release of the first black hole image became a viral sensation, spawning memes and discussions that spread scientific concepts to millions. This digital engagement brought black holes into everyday conversations like never before. Merchandising has embraced black holes as a compelling aesthetic. Clothing, posters, and accessories featuring black hole imagery have become popular, blending science with fashion and design. These products allow people to carry a piece of cosmic mystery into their daily lives. The allure of black holes often lies in their ability to blur the line between fact and imagination. While rooted in cutting-edge science, they evoke feelings of awe and mystery that transcend technical understanding. This combination makes them a perfect subject for creative expression. Their role in popular media highlights humanity's enduring fascination with the cosmos. Black holes serve as a reminder of the vast unknown, fueling both scientific inquiry and artistic inspiration. They symbolize our desire to explore, to understand, and to connect with something greater than ourselves. The depiction of black holes in popular media not only entertains but also educates. By weaving science into stories, visuals, and cultural expressions, they inspire curiosity and bridge the gap between complex astrophysics and the imagination of audiences worldwide. The first image of a black hole has inspired a wave of artwork and creative interpretations across the world. Its haunting beauty, with the glowing ring and central shadow, has become a powerful symbol for both science and imagination. Artists have embraced it as a muse to explore themes of mystery, scale, and the unknown. Painters and illustrators have reimagined the black hole's image in vivid colors and abstract forms. These works often blend scientific accuracy with artistic freedom, transforming the shadow and ring into striking visual metaphors. The interplay of light and darkness resonates deeply with audiences. Digital artists have used the image to craft immersive experiences, creating animations and simulations that expand on the black hole's visual impact. These interpretations bring the cosmic object to life, allowing viewers to journey into its mesmerizing depths. They make the science accessible through captivating visuals. Sculptors have incorporated the black hole structure into three-dimensional works, using materials like metal and glass to replicate its luminous ring. These pieces emphasize its spatial complexity, offering a tactile representation of one of the universe's most enigmatic phenomena. Musicians have also found inspiration in the image, composing pieces that capture its grandeur and mystery. From orchestral scores to electronic soundscapes, these works reflect the awe and emotion evoked by the black hole. They translate its visual power into a different sensory experience. Poets and writers have used the image as a metaphor for human experience, exploring ideas of infinity, loss, and transformation. The black hole's shadow becomes a symbol for the unknown, a space where imagination and science meet. These narratives connect cosmic phenomena to personal and universal themes. Fashion designers have drawn from the image's bold contrasts and circular symmetry, incorporating it into clothing and accessories. The black hole's distinctive shape has appeared on everything from runway collections to everyday wear, blending science with modern design. Interactive exhibits and installations have used the image as a centerpiece to engage audiences in learning and exploration. By combining art, light, and sound, these experiences immerse visitors in the black hole's environment. They provide a bridge between education and creativity. The black hole's image has even inspired cultural reinterpretations, with traditional art forms incorporating its elements. Indigenous artists and creators from diverse backgrounds have woven its visual themes into their work, connecting cosmic discoveries with their cultural narratives. Graphic designers have used the black hole's image in posters, logos, and visual campaigns. Its iconic ring has become a recognizable motif, symbolizing exploration and discovery in a variety of contexts. These designs emphasize its significance as a global icon. Children's books and educational illustrations have also embraced the image, using it to introduce young minds to the wonders of the universe. The black hole becomes a character, a gateway to understanding space and science. These interpretations make the discovery approachable and inspiring. The artwork inspired by the black hole image reflects the profound impact of this scientific achievement. It has transformed a technical milestone into a cultural phenomenon, bridging the gap between knowledge and expression. Each interpretation adds a new layer of meaning, ensuring its legacy endures across generations. Space phenomena have always captured the public's imagination, offering a glimpse into the vastness and mystery of the universe. The first image of a black hole intensified this fascination, reminding people of the wonders that lie beyond our world. It reignited curiosity about what exists in the cosmos. Events like solar eclipses and meteor showers consistently draw global attention. These celestial occurrences, much like the black hole image, provide moments of connection to the universe. They spark excitement and offer a shared experience of wonder. The discovery of exoplanets has also fueled public interest in space. The possibility of other habitable worlds resonates deeply, raising questions about life beyond Earth. These discoveries encourage people to think about the universe as a dynamic, interconnected system. Images from space telescopes like Hubble and James Webb have brought distant galaxies, nebulae, and stars into stunning focus. Each image reveals the beauty and complexity of the cosmos, inspiring awe and making the vastness of space feel tangible and real. Space exploration missions such as Mars rovers and asteroid landings captivate audiences with their sense of adventure. They remind people of humanity's ingenuity and drive to explore the unknown. These missions show how space phenomena are both accessible and profoundly mysterious. Theories about cosmic events like black holes, supernovas, and the Big Bang draw attention for their scale and implications. These phenomena challenge our understanding of reality, inviting the public to engage with questions about time, space, and existence. Popular media has played a significant role in sustaining public fascination with space. Movies, documentaries, and books about space exploration and cosmic phenomena make these topics relatable and exciting. They bring the abstract closer to home, making science accessible to all. Social media has amplified interest in space phenomena, making discoveries and events instantly shareable. Posts about new planets, distant galaxies, or the latest space missions often go viral, spreading curiosity to millions. This digital reach has brought space science into everyday conversations. Space agencies like NASA and ESA have embraced this fascination, using captivating visuals and storytelling to engage the public. Their outreach efforts make complex discoveries understandable, ensuring that people feel connected to the science. Educational programs and initiatives inspired by space phenomena encourage young minds to dream big. Astronomy clubs, planetarium shows, and STEM programs centered on space fuel the imagination of future scientists and explorers. They use the wonder of space to inspire learning. The fascination with space often stems from its ability to make us feel small, yet part of something vast. The unknown depths of the universe spark a mix of humility and curiosity, pushing us to seek answers about our place in the cosmos. Public fascination with space phenomena reflects humanity's innate desire to explore, understand, and connect. Each discovery, whether an image of a black hole or a distant planet, reminds us of the infinite possibilities that await. It keeps our eyes turned toward the stars. The first image of a black hole opened the door to countless educational opportunities. It provided a real-world example of scientific discovery that could engage students and spark curiosity. This milestone became a teaching tool for explaining complex concepts in an accessible way. Classrooms around the world incorporated the black hole image into their lessons. Teachers used it to explain topics like gravity, light, and space-time. The image made abstract ideas tangible, helping students grasp the significance of these fundamental principles. Universities developed courses and seminars centered on the Event Horizon Telescope project. These programs delved into the science, technology, and teamwork behind the image. They gave students a deeper appreciation for the process of discovery. Online platforms saw a surge in interest for space-related content. Educational videos, articles, and simulations featuring black holes became popular, reaching audiences of all ages. These resources expanded access to learning beyond traditional classrooms. Children's books and educational programs adapted the black hole image to inspire younger audiences. Through simplified explanations and engaging visuals, these materials introduced complex science to early learners. They encouraged a lifelong interest in space exploration. Workshops and public lectures offered hands-on learning opportunities. Participants explored the technology and methods used to capture the black hole image. These events allowed people to connect directly with the science and the scientists behind the achievement. Science museums and planetariums incorporated the image into their exhibits. Visitors could interact with models and simulations of black holes, gaining a better understanding of the forces at work. These spaces provided an immersive learning experience. The image also inspired interdisciplinary education, connecting physics, computer science, and engineering. Students learned how these fields came together in the Event Horizon Telescope project. It demonstrated the value of collaboration across disciplines. Teachers and educators used the story of the black hole image to emphasize the importance of perseverance and teamwork. The years of effort behind the discovery illustrated key lessons about problem-solving and determination. It became a motivational example for students. The accessibility of the image encouraged discussions about diversity in science. The global collaboration highlighted the contributions of scientists from different backgrounds. This narrative encouraged inclusivity and representation in STEM education. Competitions and challenges were created to engage students in black hole science. From coding contests to design projects, these activities encouraged hands-on learning. They gave students a chance to apply their knowledge creatively. Educational opportunities created by the black hole image continue to inspire people to explore the universe. It serves as a reminder that science is not just about answers, but about asking questions. It encourages learners of all ages to keep looking beyond what they know. The success of the first black hole image has paved the way for plans to image other black holes. Scientists are eager to apply the methods developed for M87* to new targets, each offering unique challenges and opportunities. These efforts aim to deepen our understanding of black hole behavior across different scales. One of the most anticipated targets is Sagittarius A*, the supermassive black hole at the center of the Milky Way. Unlike M87*, it is much closer, allowing for more detailed observations. However, its smaller size and dynamic environment present new challenges for capturing a clear image. Expanding the Event Horizon Telescope network is a key step in imaging other black holes. Adding more observatories, especially in previously uncovered regions, will improve resolution and sensitivity. This global effort will enable scientists to study smaller and more distant black holes. Future observations may focus on black holes in binary systems, where two black holes orbit each other. Capturing the dynamics of such systems would provide insights into black hole mergers and the emission of gravitational waves. These observations could link visual data with detections from observatories like LIGO. Intermediate mass black holes, which are smaller than supermassive ones but larger than stellar remnants, are another priority. These elusive objects remain poorly understood. Imaging them could fill gaps in our knowledge of black hole evolution and their role in galaxy formation. Astronomers are also exploring the possibility of imaging the shadows of merging black holes. These dramatic events produce gravitational waves that have already been detected. Capturing their visual features would provide a comprehensive view of these cosmic collisions. Imaging black holes in other galaxies is part of the long-term vision. Targets like Centaurus A, with its active nucleus and prominent jets, are of particular interest. Observing these objects will help scientists compare the behavior of black holes across diverse environments. Different wavelengths of light could reveal additional details about black holes. Observing in X-ray or infrared bands alongside radio would provide a more complete picture of their surroundings. These multi-wavelength studies will help answer questions about their structure and activity. Space-based observatories are being considered to complement ground-based efforts. Telescopes in orbit could avoid atmospheric interference, enhancing the clarity of black hole images. Combining data from both platforms would significantly expand observational capabilities. Imaging black holes over time to capture their changes is another exciting prospect. Tracking the motion of matter in accretion disks or the formation of jets would provide a dynamic view of black hole activity. This approach could reveal how black holes evolve on shorter timescales. Collaborations between existing observatories and new initiatives will drive these future efforts. Projects like the Next Generation Event Horizon Telescope are already being planned to push the boundaries of black hole imaging. These advancements promise even more detailed observations in the years to come. Plans for imaging other black holes build on the success of M87*, reflecting the ongoing commitment to exploring these cosmic enigmas. Each new target offers an opportunity to uncover deeper truths about the universe, expanding the legacy of this groundbreaking achievement. Improving resolution and techniques is a key focus for future black hole imaging. The first image demonstrated what was possible with existing methods, but advancements in technology promise even greater clarity and detail. Each improvement will bring us closer to fully understanding these cosmic giants. One approach to enhancing resolution is expanding the network of telescopes. Adding observatories in regions like Africa, Asia, and the oceans would increase the coverage and sensitivity of the array. This would create a more complete dataset, reducing gaps and noise. Increasing the observing frequency is another way to improve image quality. Higher frequency radio waves are less affected by atmospheric interference and can reveal finer details. Developing receivers capable of capturing these frequencies is a priority for the next phase of imaging. Space-based telescopes could revolutionize black hole imaging. By avoiding Earth's atmosphere entirely, they would produce clearer signals and enable continuous observations. Combining space-based data with ground-based observations would achieve unparalleled precision. Advancements in atomic clock technology will further refine synchronization across the telescope network. Greater accuracy and timing will enhance the alignment of signals, making it possible to reconstruct images with higher fidelity. This is essential for resolving smaller structures near the event horizon. Developing more powerful algorithms is critical for processing the massive datasets collected. Future techniques will focus on handling incomplete data and minimizing noise more effectively. Machine learning and artificial intelligence are expected to play a significant role in this evolution. Multi-wavelength imaging will add a new dimension to black hole observations. By integrating data from different parts of the electromagnetic spectrum, scientists can uncover details invisible at radio wavelengths alone. This comprehensive approach will provide a richer understanding of black hole environments. Simulations will continue to guide advancements in imaging techniques. By testing new methods on virtual models, scientists can predict their effectiveness before applying them to real observations. These simulations also help refine existing algorithms for better performance. Real-time data processing is another goal for improving techniques. Faster computation will allow scientists to analyze data as it is collected, identifying issues and optimizing settings immediately. This will streamline the observation process and increase efficiency. Upgrading the sensitivity of existing telescopes will also enhance image quality. Improved receivers and antennas can detect weaker signals, capturing more details from distant or smaller black holes. These upgrades will expand the range of observable targets. Collaborations with other fields, such as quantum computing and optical engineering, may lead to breakthroughs in resolution. Innovative technologies from these areas could be adapted to solve specific challenges in black hole imaging. Such interdisciplinary efforts are likely to drive the next wave of discoveries. Every step toward improving resolution and techniques will build on the foundation laid by the Event Horizon Telescope. These advancements will not only refine our view of black holes, but also deepen our understanding of the universe's most extreme phenomena. The future of black hole imaging is brighter than ever. Sagittarius A*, the supermassive black hole at the center of the Milky Way, is one of the most intriguing targets for future observations. Its proximity compared to M87** offers a unique opportunity to study a black hole in greater detail. However, its smaller size and dynamic behavior present distinct challenges. Located about 27,000 light-years from Earth, Sagittarius A** has a mass approximately 4 million times that of the Sun. While smaller than M87**, its event horizon is still vast, stretching across millions of kilometers. Observing its shadow could reveal critical insights into black hole physics. Unlike M87**, Sagittarius A** is surrounded by a much more turbulent environment. The motion of stars and gas near its center creates a rapidly changing landscape. Capturing these dynamics requires high-resolution imaging and precise timing. One challenge in observing Sagittarius A** is the variability in its accretion disk. The flow of gas and material into the black hole changes frequently, altering its emissions. This makes it more difficult to capture a stable image, but it also offers a chance to study these fluctuations in real time. Sagittarius A's smaller size means that light takes less time to orbit near the event horizon. This rapid movement causes changes in the surrounding environment to occur much faster than around M87**. Imaging such a dynamic region requires advanced techniques to freeze these changes into a coherent picture. Observing Sagittarius A** could help us understand the relationship between black holes and their host galaxies. As the central anchor of the Milky Way, it plays a key role in the motion and structure of surrounding stars. Its influence extends far beyond its immediate vicinity. Studying Sagittarius A** may also reveal clues about the history of our galaxy. By analyzing the material orbiting the black hole, scientists can infer past events such as mergers or bursts of star formation. This provides a window into the Milky Way's evolution. Data from Sagittarius A** can be compared to that of M87** to explore differences between supermassive black holes. Observing two very different environments allows scientists to identify common features and unique behaviors. These comparisons deepen our understanding of black hole diversity. The proximity of Sagittarius A** offers the potential to observe individual stars as they interact with the black hole. These close encounters create extreme gravitational effects, which provide natural experiments for testing general relativity. Tracking these motions could reveal subtle deviations from existing theories. Future imaging of Sagittarius A** will benefit from advancements in telescope technology and techniques. Improvements in resolution, timing, and sensitivity are essential for capturing the fine details of this smaller, more active black hole. These upgrades will enable unprecedented clarity. Observing Sagittarius A** is not just about studying a single black hole, it's about understanding our place in the galaxy. It connects us to the larger structures and forces that shape the Milky Way. Each discovery brings us closer to unraveling the story of our cosmic neighborhood. Sagittarius A** represents the next frontier in black hole research. Its unique characteristics make it both a challenge and an opportunity, promising new insights into the nature of gravity, matter, and the universe itself. Exploring it will continue the legacy of discovery begun with M87**. Imaging dynamic black hole events is an exciting prospect that could transform our understanding of these extreme objects. Unlike static observations, capturing changes in real time offers insights into the evolving processes around a black hole. It allows scientists to witness phenomena as they unfold. One key area of interest is the behavior of material in accretion disks. As gas and dust spiral inward, they often produce flares and sudden bursts of energy. Imaging these events could reveal how matter interacts with the intense gravitational and magnetic forces near the event horizon. Dynamic imaging also holds promise for studying black hole jets. These powerful streams of particles and energy can change direction or intensity over time. Capturing these variations would shed light on the mechanisms that drive jet formation and their impact on surrounding environments. The merging of black holes is another phenomenon that could be observed dynamically. These cataclysmic events produce gravitational waves and may also leave visible traces in the form of shifting accretion patterns. Imaging such mergers would provide a unique view of these cosmic collisions. Time-lapse imaging could track the motion of stars and gas near a black hole. Observing their orbits and interactions over time offers a way to map the gravitational field in detail. These studies provide direct tests of general relativity in extreme conditions. Dynamic observations could also reveal how black holes feed. Periods of increased activity, known as accretion bursts, could be captured as they happen. These events show how black holes grow by consuming material, offering insights into their life cycles. Advancements in technology are key to achieving this goal. Faster data collection and real-time processing will allow telescopes to capture changes on short timescales. These improvements are essential for studying smaller, more active black holes like Sagittarius A*. Multi-wavelength observations will enhance the ability to track dynamic events. By combining data from radio, X-ray, and optical telescopes, scientists can observe multiple aspects of black hole behavior. This approach provides a more comprehensive picture of their activity. Dynamic imaging also opens the door to studying rare and transient events. Phenomena like tidal disruption, where a star is torn apart by a black hole, occur over relatively short periods. Capturing these moments offers a glimpse into the most dramatic interactions in the universe. Theoretical models will play an important role in interpreting dynamic data. Simulations help predict how black hole environments should behave over time, providing a framework for understanding real observations. These models guide the search for specific phenomena. Collaboration between observatories is crucial for imaging dynamic events. Coordinated efforts allow telescopes to track changes continuously, covering different angles and time zones. This global network ensures no critical moments are missed. The prospect of imaging dynamic black hole events represents the next evolution in astronomical observation. Each captured moment tells a story of change, activity, and interaction, bringing us closer to understanding the complex lives of black holes. It is a frontier filled with potential discoveries. Innovations in telescope technology are driving the future of black hole imaging and exploration. These advancements enable scientists to observe the universe with greater clarity and precision, pushing the boundaries of what is possible. Each breakthrough brings us closer to unlocking the secrets of black holes. The development of more sensitive receivers is a key innovation. These devices can detect faint signals from the most distant objects, capturing details that were previously impossible to observe. Improved sensitivity allows telescopes to study smaller and less active black holes with precision. Higher frequency capabilities are another area of advancement. Observing at millimeter and submillimeter wavelengths reduces atmospheric interference and reveals finer structures around black holes. These frequencies are essential for capturing the intricate details of an event horizon. Adaptive optic systems have transformed ground-based telescopes by compensating for distortions caused by Earth's atmosphere. These systems use real-time adjustments to sharpen images, enabling astronomers to see cosmic phenomena with unprecedented clarity. Space-based telescopes offer another path to innovation. By avoiding atmospheric interference entirely, they provide a clear and stable view of the universe. Future missions may deploy telescopes designed specifically for black hole imaging, expanding the range and resolution of observations. Interferometry, the technique of combining data from multiple telescopes, continues to evolve. Improvements in synchronization and data processing are enhancing the resolution of these virtual arrays. These advancements allow telescopes to work together as a single, planet-sized instrument. Miniaturization and modularity in telescope design are opening new possibilities. Compact, lightweight components make it easier to deploy telescopes in remote locations or even in space. Modular systems allow for upgrades and customization, ensuring that technology keeps pace with scientific goals. Machine learning is playing an increasing role in telescope technology. Algorithms trained to identify patterns in noisy data are helping to filter and enhance observations. This approach speeds up data analysis and improves the accuracy of imaging techniques. The integration of quantum technologies is on the horizon. Quantum sensors and communication systems could revolutionize how telescopes detect and share information. These tools promise to enhance the precision and efficiency of future observatories. Collaboration between disciplines is driving innovative designs. Engineers, physicists, and computer scientists are working together to address specific challenges in black hole imaging. Their combined expertise is leading to creative solutions that push the limits of technology. Global networks of telescopes are benefiting from advancements in connectivity. Faster and more reliable data transfer systems are enabling real-time collaboration across observatories. This connectivity ensures seamless integration of data from multiple locations. Each innovation in telescope technology builds on the achievements of the past, laying the groundwork for future discoveries. These advancements are not just improving our ability to observe black holes, they are reshaping our understanding of the universe. The tools we develop today will define the possibilities of tomorrow. The journey through the first image of a black hole has been nothing short of extraordinary. We explored the groundbreaking moment when the Event Horizon Telescope captured the shadow of M87*, providing humanity's first direct view of a black hole. This achievement confirmed decades of theoretical predictions and opened new doors in our understanding of the universe. We discussed the immense coordination required for the project, from synchronizing observatories around the world to processing massive amounts of data with cutting-edge algorithms. The teamwork and international collaboration that made this possible demonstrated the power of science to unite people across borders and disciplines. The significance of the black hole's shadow was also a key focus. It validated Einstein's general relativity under the most extreme conditions and offered insights into the nature of accretion disks, jets, and the bending of space-time. Each detail of the image deepened our knowledge of how black holes shape the cosmos. We explored how this achievement has influenced not just science but culture. From inspiring artists and musicians to engaging millions through media and educational outreach, the black hole image transcended its scientific origins to become a global symbol of discovery and imagination. The educational opportunities it created have inspired a new generation of students and enthusiasts. It brought complex ideas like gravity, light, and space-time into classrooms and living rooms, making science more accessible and exciting for everyone. Looking ahead, we discussed the plans for imaging other black holes, including Sagittarius A** at the center of our galaxy. Advancing telescope technology and imaging techniques will enable us to study dynamic black hole events and even capture the shadows of merging black holes. The ongoing innovations in telescope design, from higher frequencies to space-based observatories, promise even greater clarity and resolution. These advancements are crucial for exploring black holes of all sizes and studying their impact on the universe. Throughout this journey, one theme stood out: the boundless curiosity and determination of humanity. The first black hole image is more than a scientific milestone. It's a testament to what we can achieve when we come together to push the limits of what we know. If you enjoyed this video, don't forget to like, share, and subscribe to our channel. Your support helps us create more content that dives deep into the mysteries of science, space, and the universe. Be sure to check out the rest of our videos for more fascinating stories and discoveries. Together, let's keep exploring the wonders of the cosmos and uncovering the secrets that lie beyond the stars. Thank you for watching, and we'll see you next time.